आपका साउंड डायरेक्ट सुना रही। हेलो 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 हाँ हाँ हेलो 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 सुना पीपीएस लिखा है रंजीत राव हेलो ओहो चलो तो यहाँ पर लिख दो कि प्रोग्रामिंग स्टार्ट है किसमें यूट्यूब पे और मैं लिख के दिखा दूँ ना तो
देख देगा आपका
टाइम लैग हो जाएगा
है Good afternoon, sir. Srikant sir, good afternoon.
Yeah, good afternoon, Professor Srini.
Yes. No problem.
Yeah, I think link is working fine. Sir, actually आपका ये नहीं चल रहा है सर, म्यूट है सर.
Oh. Okay.
Hi, Professor Rajiv.
Yeah, good afternoon, Sujita. Good afternoon. Good to see you.
Rajiv ji is there. Rajiv ji, good afternoon. Akhilesh is there. Good afternoon. Good afternoon.
Good afternoon, everyone. Good to see
Yes.
several of you.
Akhilesh, audio is working.
Hello, good afternoon, everyone.
Yes.
Good afternoon,
Hello,
Akhilesh.
Rajida. Good afternoon,
Guru.
Rajida. Yeah. Professor Srini, good afternoon.
Good afternoon. Yes. Yeah, it is working.
Yeah.
I think it's 2:30. Should we start now? Am I audible, by the way?
Yeah.
Yes.
So let's start. Good afternoon, everyone. It's my pleasure to welcome to the two-day workshop, Recent Advances in Inorganic Chemistry, RAIC 2022. Let me close this. Okay. Yeah. Okay. The workshop is sponsored through the Scientific and Social Responsibility Scheme by the Science and Engineering Research Board of India. The eWorkshop aims to share the recent advances in the field of inorganic and materials chemistry. This will showcase the frontiers of research areas in the novel molecules and materials and their applications in catalysis, photocatalysis, optics, magnetism, drugs, diagnostics, etc., as well as the fundamental insight into these aspects. About the details of our IIT Bhubaneswar and the School of Basic Sciences, I'll request, and as well as about the conference, I'll request Professor Sujit Roy to welcome everyone and introduce these things to the audience. Professor Roy, please.
Yeah. Am I audible?
Yes, sir.
Yes.
Yeah. Okay. Welcome to all of you, the speakers, the distinguished speakers who have agreed to be part of this RAIC. And I believe across India from Mumbai to Bhopal and then Delhi to Bangalore. All the distinguished speakers would be joining this conference and share their work as well as guide the young MSc students and other students, research scholars, give them direction in the area of latest advances in inorganic chemistry. We very rarely hear separate symposiums for inorganic chemistry, and it is a delight. I'm delighted that this small event we have been able to do, focusing on inorganic chemistry. So, on behalf of the administration, the school, and on my personal behalf, I welcome all these speakers who would be deliberating this today and tomorrow. A special welcome also to the registered participants which have which have grown beyond 250. We didn't expect so many students will register. So welcome to all of these students who have registered for online viewing of this workshop. IIT Bhubaneswar is obviously a 2G IIT, and we started in 2008 in Kharagpur, then 2009 from Bhubaneswar. Since 2016, we are in a one campus. Obviously, it's a beautiful campus, and you can see our website in order to appreciate the different departments and the other facilities that have developed over these years at IIT Bhubaneswar. This, like any other IIT, we also have engineering and different departments, but science, interestingly, is just under one roof. Today only our first director, Professor Chakravarti, visited us. So we were discussing why you have kept all the science together. So physics, chemistry, and mathematics, all under one head. And we realized this, that by being under one umbrella, there is a possibility of this cross-talk, which normally doesn't so much happen in, especially in a small institute where departments are there and they are separated out too much. So talking to each other is not so much. So we have that privilege of next door. Some noise from somewhere coming. Hello. There is a noise I can hear. Hopefully it will be resolved. Maybe somebody has joined, and can I continue? Yeah, no, fine. So we realize that we have that privilege of being in one under one roof and sharing with our excitement with our colleagues in physics, mathematics as well. In talking about a chemistry department or chemistry discipline under basic science school, we're a very small discipline now with 12 faculty members, and these 12 faculty members are entrusted with taking care of BTech, MSc. We have a 2-year MSc program, which started right from the beginning, and the PhD program as well. And these faculty members have come from various corners of the country, having most of their educations, one of the education in one of the IITs definitely, and all from having their education abroad, postdoctoral studies, etc. abroad. So our website gives a list of these faculty members' names. And broadly, we have synthetic organic, synthetic inorganic, then faculty members both in organic and inorganic looking into materials, and then some of us looking into catalysis, and also the faculty members in looking into bio aspects like biosciences. We do have one member who is absolutely trained in bioscience. So that is yet another specialty of our department. It truly gives a flavor of interdisciplinary nature of this department. So all these faculty members have really right from beginning have struggled pretty hard to be first in one campus, then to another campus, then this is the final campus where we are. So 3 different campuses, these faculty members had to shift their laboratories. And all of you know, being in chemistry, how hard it is for somebody to keep moving their laboratory infrastructure from one to other. But fortunately now we are housed in under one roof in Orugun, which is about 30 kilometers from the airport. And very nearby we have NICER, and very nearby we have the Institute of Chemical Technology, ICT. So that there is a scope for collaboration and crosstalk with them as well. And besides teaching, the faculty members are also active in research. I was just looking through, being a Dean R&D, I was just going through some data, and I found that faculty members have been able to carry out projects worth more than 8 crores. Okay, that shows that all of them are very active, and in terms of number of publications, it's more than 300 now. Okay, our MSc students obviously are going to all the places abroad as well as within India, to many of your labs who are senior people and their laboratories for their PhD. And the PhD students are also going to industry as well as the academia, which it's there. So that's all about the chemistry, and we will be delighted to hear the presentations by the various speakers, as I have told. So with this, I would again like to welcome all of you for being able to be a part of this workshop. And we must thank DST for supporting this workshop, and we expect a very good interaction during this 1.5 days. I see Dr. Lahiri, so hello, Dr. Lahiri. Yeah. So once again, welcome to all of you, and Srikant, Dr. Srikant Patru would like to take over. Srikant, yeah. Hello, Srikant, yeah.
Thank you. First of all, let opportunity. Thank you all to be present here, and also let me once again welcome all of you in this auspicious program. Because why I am telling, because this is the first time we are able to do something, at least from the chemistry and bioscience group at IIT Bhubaneswar. So we tried to conduct this symposium, another symposium earlier, but because of this COVID-19 pandemic, so it was very unfortunate to just kind of skip it actually. But anyway, so better something is there than nothing actually. So at least let us just get some of the flavor of this in terms of eWorkshop. So it could really be very good actually if we can physically meet with everyone actually, all the speakers and other things. So thank you all, and it is really, again I am telling, as we are just conducting the first time. So and also Professor Roy already mentioned about the department, about a little bit history about IIT Bhubaneswar and how things are going on. So I will just little bit talk about the workshop. At the workshop, we are just keeping the theme a little bit broad, considering the heterogeneous audience, because we are just trying to reach to at least school, college level students, BSc or MSc level students, so that if we can send some of the message of flavor of the research, so I feel that is going to be good. So that is why this is one of the primary concern for us to keep these things in a broader way. And also we keep the idea that most of the content of inorganic chemistry or different areas of inorganic chemistry we can at least cover in this workshop. So this is basically the idea, and already Dr. Kaushik mentioned a little bit about the topics, what basically is going to be covered. So now let me take the opportunity, or let me just talk about the session and take the opportunity to introduce the speaker also, because this session actually we have divided in 3 technical sessions. So technical session 1 will be conducted today from 3 p.m. onwards. Then tomorrow we are going to have 2 more technical sessions. The session 1 will start at 9:30 onwards, and the technical session 2 will start at 3 p.m. onwards. So today our program will actually start with something fundamentals and also computational aspects of inorganic chemistry. And there we are going to have renowned scientists or professors. So I do not need to mention their name. So we have Professor G.K. Lahiri, and let me just tell few words, because he was my he is my PhD supervisor actually. So it is really going to be a great honor for me to invite him. Okay. Secondly, we have Professor Rupam Dinda from NIT Rourkela, then Professor Movin from IIT Indore, and the conclusive session, today's conclusive session, we have again another renowned professor, Professor P.K. Chattaraj from IIT Kharagpur. And this session is going to be chaired by again another popular scientist, Professor S. Srinivasan from Niger, Bhubaneswar. So in tomorrow's session, actually will be again start at 9:30, and that will be chaired by Professor V.R. Pedireddy from IIT Bhubaneswar. And in this session, we just try to see actually from the speaker something the advancement of inorganic chemistry in the area of supramolecular structure and also catalysis aspect. And there we are again going to have 3 renowned speakers, Professor Parthasarathi Mukherjee from IISc Bangalore, then Professor Debabrata Maiti, the very dynamic person from IIT Bombay, and then another person from ICT Mumbai, that is Professor Anand Kapdi. And in the technical session 3, we'll start at 3 p.m. tomorrow, and that will be chaired by Professor V. Kari from IIT Bhubaneswar. And there we are going to have again 3 more scientists. Okay, so they are going to show something again, the application, some biological aspects of inorganic chemistry. So that is Professor Rajiv Gupta from Delhi University, then Professor Apurvalal Konar from IISER Bhopal, and also Professor A.K. Singh, my colleague from IIT Bhubaneswar. So in this symposium, we basically just planned, and I think also we have requested our speakers to just shed on lights on the fundamentals, so that the undergraduate student or the students who are at BSc or MSc level, they also can correlate the inorganic chemistry research, and they can get interest in that area. And I am very happy that all the presenters or all the speakers have accepted our request, and definitely they are going to do that one. And finally, I would like to first thank all the speakers for acceptance our invitation in spite of their busy schedule. Then I would like to thank our Department School of Basic Science, then R&D section, for giving any kind of technical and administrative support to just conduct this workshop. Then I would like to thank the SERB, okay, for giving the financial support to conduct this workshop under the very nice social scientific initiative scheme. And also I would like to thank my colleagues, okay, so without whom actually at least we could not able, whatever we are trying to do, which it could not be possible. And then my dear students, and also the participants. And I am really happy to inform all of you that there is almost 320 students registered for this workshop. And I think all of them are going to be definitely benefited with this attending this symposium. And with this, I would like to thank you all. And I'd like to just kind of concluding my talk. And And I just let me inform you that we will start our technical session at 3 o'clock. So let us take a short break and we'll come back at 3 o'clock. So thank you all. And again, let me welcome all of you to this eWorkshop RAIC 2022. Thank you.
So as Dr. Patra mentioned, we'll take a quick break now for about 10 minutes. And we'll meet once again at 3 o'clock and we'll start the technical session. Okay, see you once again then at 3 o'clock. Thank you.
My job is to make college easier because students have a lot.
Sorry, Coach.
Good afternoon, everyone. Welcome once again.
This
So
video,
we are going
I'm
to
gonna
start
show you how you can enable live
day
chat on the
1,
YouTube
session
live stream.
1.
So you can see I'm in the back
So,
end of a YouTube live stream. And I'm
Professor,
going to show you how you can enable a live chat so that you can engage with your viewers. So all I need to do for
Akhilesh.
this is click on the edit over here, and you'll then see all of these features. So this is where you normally change this setting, but you'll see that it's not showing up in here.
But before
So
we
you're gonna
start
click
this
on
thing,
cross,
let me
click
just
on the live stream
introduce some
settings
technical
icon in
details.
the top right corner.
All the
And then
listeners, all
here's
the
where you can
audience,
see
they will
live
be
chat.
listening through the
You
YouTube
can
link
see
that we
details,
have shared.
monetization,
And there is a live
Click on
chat
live
session.
chat, of course.
They
And
can,
then at the top, you'll see enable live chat.
hold on, let me
And that's
mute.
pretty much it. You can also allow live chat.
There's a
to
live
play
chat
if you want
session.
to.
They can write
Click
their
save,
questions,
and there we go.
and the chair will
That's
pick
how
up
you
the
can enable
questions
live chat on
and
the
read
YouTube
it to
live
the
stream.
speaker,
It's that
so that the
simple.
speaker can
There you
answer
go.
at the very
So
end.
this is the live
So I'll now
stream
hand it over
with
to
these features, right?
Professor
So this-
Akhilesh Singh.
click on
He will
edit
introduce the
over
chair,
here,
and then the session can start.
and you'll then
Thank you.
see all of these features, right? So this is where you'd normally change this setting.
Thank you, Professor
But
Samanto.
you'll see
So,
that it's not showing up in here.
it
So
gives me happiness to introduce Professor A. Srinivasan. He happened to be my super senior at IIT Kanpur. So he was working there in porphyrin lab, with Professor K. Chandrasekhar, and he is one of the earliest faculty member of NICE since it started. And right now he is working in the area of photosensitizers for PDT applications, metallurgy. You please continue to chair this session. Okay, now you can start. Thank you very much.
Yeah. Thank you, Akhilesh, for the nice introduction. First of all, I would like to take this opportunity to thank the organizing committee members, particularly Professor Sujit Rai, Dr. Srikant Pastra, and Akhilesh Ayosha for giving me the opportunity to chair this session. On behalf of the organizing committee, I also welcome all the delegates and the speakers and students. Good afternoon to all. In this session, we have 4 lectures. The first speaker is Professor Gautam Kumar Lairi. It is a great pleasure for me to introduce Professor Gautam Kumar Lairi. Professor Lairi did his PhD from IICS Calcutta. He was a postdoctoral fellow at West Virginia University, United States. Soon after his postdoctoral research, he joined as an assistant professor at IIT Bombay in 1993. Since 2001, he is a professor at IIT Bombay. Professor Lairi is well known to most of the colleagues, and no formal introduction is necessary. However, for the benefit of the younger students, I wish to highlight some of the awards and recognitions received by Professor Lairi. He is the fellow of all the 3 Academy of Sciences, that is Indian Academy of Sciences, Bangalore, National Academy of Sciences, Nashik, and the Indian National Science Academy, New Delhi. He received the J.C. Bose Fellowship in the year 2019. From his long award and recognition list, I impressed one award, that is Excellence in Teaching Award at IIT Bombay for the year 2010 and 2015. In addition to excellent in research, receiving twice the Excellence in Teaching Award is something exceptional, and it is a dream for every individual in this profession to achieve this award. His research interests are electrochemical, spectroscopic, magnetic, structural, and theoretical manifestations of delegate intramolecular valence and spin state interactions at the interface of redox-sensitive metal ligand frameworks and catalysis. With this brief introduction, may I now invite Professor Gautam Kumar Lairi to deliver a lecture on electronic structure and reactivity of non-innocently behaving ligand-derived system. Sir, the floor is yours, sir.
Yes, Professor Srinivasan.
Sir.
So nice to see you on the screen.
Yes.
And of course, hearing you
Yes.
after a gap of, I think, few months.
3 years.
Not 3 years. In between, we met on the screen during the selection committee. No?
Yes, exactly. Sir.
How is it?
Yes,
How is everything?
Yes. Yeah, going on fine, sir. No problem. Yes.
So nice. So
Sir. Yes, yeah. Thank you, sir. Okay.
So formally, let me begin by expressing my gratitudes and thanks to the chairman of this session and of course the organizers to invite me, and I feel very happy to share some of our research work towards the audience of this particular conference. Now I understand this audience is mostly students oriented. I would like to concentrate more on the fundamental issues about the kind of things what we are pursuing at IIT Bombay. Now, if we look at the title, it essentially covers 3 areas which are closely interlinked to each other. So, we are essentially dealing with the molecular system, where of course you have the transition metal, and that metal is linked to conventionally or little bit unconventionally, unconventional type of ligands, what we call the redox active ligands. And under that circumstances, what would be the electronic structural aspects at the metal ligand interface? That is one of the targets. And once it is being ascertained to a reasonable extent, then we try to look into the fact of the reactivity aspects again at that interface. Okay. Now, let me put it this way, from the very basic principles of the ligand. Now, if you look at the literature or inorganic chemistry in general, you would be seeing that numerous type of number of ligands people have been used over the centuries, right? And in most occasions, the ligands are essentially redox inactive. That means they do have only one oxidation state. But around last 50 years, people have recognized that there are few ligands which could have exhibited more than one oxidation states, like the transition metal ions. And there is a very standard proverb, that variable valence actually pervades the chemistry of transition metal ions. And if you have a particular type of ligand which can also exhibit more than one oxidation state or redox states, and then if you put this metal and that sort of ligands together, then essentially you are introducing a kind of competitiveness in the system where you need to figure it out before going into any other reactivity aspects, that electron transfer is happening at what point, at the metal side or at the ligand side or at the or in a mixed situations. Because what happened, if the frontier orbital energy of metal and this sort of ligands is close to each other, then any of the components may participate in the electron transfer aspects, right? So that's a little bit sensitive issue to figure it out, at least experimentally, what we call the physical oxidation state. Now, if you look at the biological system, there are many such ligands exist, so there is a need to understand how they behave. Okay. Now, if we take up the few conventional redox active ligands, for example, the nitrosyl, or you see the quinone setup, or even if you look at the azo-based setup, you would be seeing that they have multiple oxidation states possible, like quinone to radical to the fully reduced state, or we call it super reduced state. Similarly, nitrosyl can have the nitrosonium and nitrosyl radical, and remember, nitrosyl radical is the only radical where you would see that is a neutral radical. Most of the radicals are either cationic or anionic, and you would be seeing nitrosyl anionic state. Of course, one more state is possible, which I am not going to talk about. And quinone, the similar situation you will have is to super reduced via the radical state. Okay. Now the good point is that which particular state exists in your compound, particularly the metal complexes what you are talking about, that could be easily understood if you have the structural information, particularly the bond parameters, the diagnostic bond parameters, okay, bond parameters which can vary, reasonably based on the redox state. For example, if you go for the quinone to, doubly reduced state via the intermediate radical state, you will see the CX bond distance. This is the characteristics bond what one could follow as a function of the redox state. You will see this bond parameter would be 1.2 to 1.3 to 1.34. So if you have a good crystal structure, good quality crystal structure I'm talking about, then looking at this bond distance, this particular bond distance, you could guess what is the redox state of that redox active ligand in your compound, and then you can figure it out the rest of the things and the physical oxidation state of the metal ion. Now, if you have a situation like this, then in many occasions, instead of having any precise description of the redox states of the metal and ligand, you may end up to a situation of a resonating form or in a tautomeric form. For example, this particular form could also be well defined by following the intramolecular electron rearrangement. That means one-step metal oxidation could lead to one-step ligand reduction or vice versa. Similarly over here, and it could follow either resonating route or the tautomeric route. Now, many occasions experimentally is very difficult to figure it out what particular state is involved in the process of the either at the reaction level or at the biological processes, and at that circumstances one need to depend on variety of experimental and theoretical studies, and in certain instances the intermediate description fits better than any precise description. So it's a bit sensitive issue. Now, if we move to the dinuclear setup, situation is rather complicated, more complicated, I should say. For example, if you start with a neutral ligand bridge dimetallic isovalent situation and allow the system to undergo, say, 1 electron oxidation, the oxidation could take place at the metal site, which would take you to the mixed valence situation, or it could take place at the bridge site, then you would have the radical bridge isovalent situation, or it can happen a RAIC process, that means it's called the redox induced electron transfer, where you can think about two-step metal oxidation complemented by one-step ligand reduction. So eventually you end up with the radical bridge higher analog. So all sort of possibilities one could conceive. It is easy to write on a piece of paper, but once you try to figure it out by experimental or theoretical means, it's a whole lot of job one needs to find out. It requires a lot of experience, a lot of experimental features, etc., etc. So we have been addressing these issues since decades, and one could that is my understanding, that if you have all the experimental data along with the quality or good quality theoretical support, you can reach to a reasonably acceptable situation. One cannot say this is the 100% correct configuration, but you could reach to a acceptable situation where your contradiction is not too much, but still some contradictions would be there, because and then you need to look for a better spectroscopic technique in the sense of the time scale of that spectroscopic technique, because it's a very fast electron transfer situation. So all sort of issues are there. So we are not going to discuss all these issues at length. What we are trying to talk about, that if you have a situation of such where you have the metal and ligands in a particular assembly, and then you need to figure it out how the intermolecular electron transfer or charge transfer going on over there, and what would be the valence situation at the interface. As I said, there are two issues parallelly move on over there. One we call the resonating configuration, other is the tautomeric form. It sounds easy, but in practice you will see a lot of difficulties are there, and there our task is to figure it out. For example, I will take a couple of cases to explain that issue so that you may have some better perceptions about what I am trying to highlight. So I am taking a very simple system, say one azoaromatic derived system if you take, and all of you know with a very basic inorganic, or you could say organic chemistry also, that azo system if you start with, it can successively accept 2 electrons, then it moves to the doubly reduced hydroxide form via the intermediate radical form, and then it can also accept 2 more electrons, and then this nitrogen-nitrogen bond clips. Okay, that's a separate issue. Now, if you look at the bond distance, azo bond distance, which is very characteristic to his redox states, and there is no way to miss it. Starting from, if you take the free azo, that will be around 1.25 angstrom. But as soon as you attach to a metal center, then pi back bonding takes place, and lengthening of azo bond happens, and it can go up to 1.3 without the charge transfer. That because of the pi back bonding, not the charge transfer. And then if the charge is transferred, then it can go up to a 1.35 to 1.38, which is called to the radical. But you have to establish it by experimental technique that truly it is a radical. And then further lengthening would give you the hydroxide form, and there you can see the bond distance 1.4 and above. Now, if we consider a dinuclear setup where the isovalent metal centers are bridged by, in a generic sense I'm talking about, bridged by a neutral ligand, right? Now you are allowed to photoirradiate, allow the system to undergo the MLCT. Then without any electron transfer, it will happen only the reorganization of charge within at the intermediate. Then what will happen, that metal electrons, the reduced state, metal N means reduced state, it will move towards the ligand antibonding orbital, because the pi star orbital is close to the metal d pi orbital. That's why I said that energetically should be compatible, the frontier orbitals, and also symmetrically compatible. Both the factors are equally needed to have the charge transfer. We know all these things. So that if the electron transfer from metal to the ligand side, then you have a situation of a mixed valence, right? That means the radical bridged, what we call about the radical bridged mixed valence situation. Okay, and this we define as I'll not discuss at length this particular issue, and this electron transfer then this radical bridge isovalent situation could also be defined at the localized concept or by a delocalized concept. That means this one electron which could be delocalized between the two metal centers, or it could be localized on a particular metal center depending on the electron transfer rates and also the solvent effect, etc., etc. So many issues are there, but the two alternatives are there. And if we allow the system to undergo one more, photoirradiation, that means the double, charge transfer, then what will happen? That one more metal, the second metal ion, will also undergo the electron transfer between the metal and the ligand at the electron metal ligand interface. So you will be getting, that doubly reduced ligand bridged higher isovalent analog. So two-step intermolecular electron transfer is taking place. These are not outside you are putting any electron over here. This is an intramolecular electron transfer, and that is being feasible since both the metal and ligand can have the propensity to stabilize in different oxidation state. So this is a unique class of ligand. In the common ligand, if you take, their ligand can only stabilize in one oxidation state, and there you cannot have this sort of situations. Okay. Now to understand this phenomena in a little bit broader sense, we have chosen a few type of azoaromatics. Now if you look at the situation, that if we go for this oxazole being thiazole based this azoaromatics, and if you react with one electron rich starting material or metal precursor, say ruthenium acetyl acetone, very popular starting material, then we get three products together. Okay, in one product, what you could see that it is the first situation, what I have said over here, that one-step electron transfer between the metal and the azo interface, and we get, a kind of radical bridged mixed valence situation in a localized fashion. And if you look at that azo distance, which is 1.376, it is the domain of the radical. There is no confusion about that. Now, it also gives us another product where you could see the azo bond distance lengthened further to 1.418. That does mean the two-step IET component. Okay. So does it not mean a valence tautomeric situation? So both the things could be isolated from the same reaction pot and could be structurally and spectroscopically as well as magnetically be characterized. And then additional, because of the low potential over here, okay, redox potential I'm talking about, then this particular component could also be oxidized to give us that, radical bridged higher analog in terms of isovalence. That means this NN2- would be oxidized one step, okay, by giving us the RU3 bridged by the radical state. So we could manage to see one particular issue which people have not seen so far, that is the MLCT excited state could also be stabilized in the ground state. And that is because of the kind of ligand framework we have chosen, and energetics are such which enable the system to stabilize at the ground state through the MLCT, excitation process. Okay, and there both the IET system, intermolecular electron transfer, both the state could be isolated in a very precise manner, and which could be manifested by their structural characterization, as you could see it. And here you see that bond distance again goes back to 1.35, and which corroborates the fact of a radical based azo function over here. Now, if we look at sometime back, we have started with this particular ligand, which is called azo-bispiridine. And recently we have introduced this particular ligand where the bench thiazole we have used, and along with that, this relatively, electronically rich at this setup. Now, what happened as a dinucleate system, this compound ends up with a radical bridged mixed valence situation. That means one-step IET process. Now, if you go to the other extreme over here, this is the, among the three, this is the better electronically donating group is there, and it gives us the straightaway the two-step IET product over here. But once you get the intermediate, this particular ligand, we get both the things in almost 50-50%. That is called the valence tautomeric product. That means one step versus two step. So it's a very systematic movement. So whether one would be getting the one step IET product or two step IET product, or both one and two step together in the form of a valence tautomer, that depends on the electronic nature of the aromatic function you have linked to the azo function. Okay, so this is how it is so. And one point you must have noticed, I have mentioned in between, that the free azo distance is around 1.2 to 1.25 roughly, and which is lengthened to a certain extent through the pi back bonding, but without charge transfer, and that the bond order experimentally one could figure it out of 1.30, and when the charge transfer takes place, the bond order lengthen further, and it can go greater than 1.35. So there is no experimental verifications of that in a particular system. So you could manage to get one copper system using this benzyl based ligand, and you could see, without going details, in the structural discussion, etc., etc. I would like to project it over here. This is a very unique molecule in the sense that the two copper centers are bridged with the three same ligands. I'm talking about this ligand. And out of the three ligands, two ligands are linked through the nitrogen, this nitrogen and the azonitrogen, and one particular ligand where the azo bond is free. And you look at this azo bond distance is the 1.265, which is behaving like a free ligand. And the other two azo bond is coming close to the 1.30, and that essentially establishes the long-standing fact, which there are no structural proof within a particular molecular unit that bonded and non-bonded setup would have, and that justifies the fact of the back bonding instead of any charge transfer, because any charge transfer from metal to ligand, okay, if it takes place, then further lengthening takes place beyond the 1.35 angstrom. That is the standard value what we could establish so far. Now, if you see, if what we have been talking about, if that concept is correct, we thought to re-examine the whole thing in the context of MLCT versus non-MLCT, then how it functions. So we prepared the three compounds looking at the same ligand framework, and you see that there are three compounds we have taken. In one compound, you have the electronically rich ACAC function. I'm talking about the terminal ligand or NCA ligand. And in other case, we have taken very strong pi-accepting azopyridine ligand and moderately pi-accepting bipyridine ligand. And all three cases composition more or less same in the sense that mononuclear, that one such ligands are there. That means this NN bonded. And if you see in all the cases, we could stabilize the radical state of this ligand. Now here one could argue the way we have tried to establish or presented so far that MLCT induced, radical formation. That means intramolecular charge transfer from 2 to azo function gives us the radical and it gets reduced to the RU3 state. But here, because of the strong pi acceptor ligand, metal cannot get oxidized to the 3 state. But still we could manage to get the radical, and then we just try to understand this phenomena. How come this non-MLCT based radical formation takes place? Because experimentally you could see the bond distances very, very characteristics of the radical state of the azo function. So, and then you have noticed the reaction takes place only in the protic solvent. Okay, and that's why we could manage to trace that, if we do the reactions in alcohol, the aldehyde could be traced from the reaction vessels. That means the solvent mediated reduction of the azo function takes place under the present circumstances where MLCT cannot operate. So the conclusion is very clear. If the molecular framework does not extend the necessary support to undergo the MLCT, then solvent could also function as the probable reducing agent over there if it is aprotic solvent. Okay, so both the factors we have portrayed in a very clear-cut fashion through the molecular fabrications. Now let us move into the fact of why we are trying to understand the electronic structural aspects of this sort of metal framework, because of two reasons. Because if you look at the earlier days catalysis, even today's catalysis, mostly from the inorganic point of view, the metal plays the effective role and ligand participates as a ligand extends as a support system, and they're basically non-spectator role of the ligands. But in today's context, situation has changed a lot, where ligand can also take part in catalysis along with the metal centers or molecular functionalization if you have the redox active ligand, and then that setup can act as an electron sponge. So it can hold the electron and can release or can accept depending on the fact of the necessity. Okay, so let us give few examples what we have been following. There are many such examples are available in the literature. We have been also trying to follow a certain issues. So if we follow these two particular catalysts, They are more or less identical. It's a diamine based catalyst. Here the acinaptine fragment is there. Now if you try to oxidize this amine, what we see, this catalyst takes us to the nitrile point, and this catalyst takes us to the imine point or transaminations. Now how it is being going on? Now if you look at their electrochemical feature without even understanding much about this thing, you can tell us that this particular ligand allows its reduction to take place in a facile fashion compared to this one. You look at the potential and the reversibility and irreversibility. So with there are a lot of issues are there. Keeping all these things aside, what you can try to say, if phenanthrone based ligand, it allows the reaction in presence of standard protocols, tempo, oxygen, all sort of things. From organic point of view, it is nothing very difficult. So we understand this thing. Then tempo first attached through this particular cycle. Okay, you probably understand the role of molecular oxygen, tempo, hydride transfer, the tempo gets in. Then your amine links over here, then beta hydride elimination, you get the imine, and then transamination. Okay, that is very simple. But if you go to the Bayan based acinaptine derived catalyst, then the same cycle goes on up to this, and then you get the imine part. Then one could think about this imine can again participate in the second cycle in the same fashion, and then eventually through beta hydride elimination at the last step, you could get nitrile, which is very simple from organic point of view. But the question is, why this catalyst allows the second cycle, why it fails over here? The reason what we could anticipate that because of the redox facile feature of this acinaptine fragment of Bayan, it allows that resonating form the way it is been written. That means intramolecular electron transfer from metal to the Bayan side. As a result, Ru2 neutral Bayan could be written as Ru3, metal would be oxidized one step, ligand would be reduced one step. So this radical, and then one could anticipate that this more electrophilic feature of ruthenium 3 at the intermediate allows the second phase attack, and that led to the nitrile function. Now here, this particular resonating form does not exist as because of the this difficult reduction of the phenanthrone fragment over here. So therefore the second cycle cannot operate. So this particular example tells us very clearly that if you have the redox active derived metal ligand based catalyst, then you may expect to have intramolecular charge transfer at the metal ligand interface, and which could make the metal metal based catalyst, that metal more electrophilic, and it can allow the substrate to attack in a better fashion or in a double fashion to give, in this case is a double fashion, to give a different products compared to where this electron transfer is not so facile. So what we have said in the previous few slides, that this IET process, which could lead to have a better catalytic event as well as the molecular functionalization event. I have just shown one catalytic event. Let us show a few functionalization event, then you would realize it. You see that if you take this 2,2-pyridine analog, okay, it could be oxygen, it could be nitrogen, right? Now, if we try to react with the earlier metal, electron-rich metal fragment, we could get the dimeric product for both oxygen and nitrogen case. Now, nitrogen case, it gets fixed up, very stable, nothing happens in presence of oxygen. Now, dioxygen case, what happened in this case, this product could also be isolated, reasonably stable, but if you allow the product to expose to the molecular oxygen, you see that oxygen activation and this CC bond cleavage, which would lead to have your picolinate product from this. Question is how it is forming, why it is not happening in the imine derivative. Now we try to understand this more or less theoretically, I should say. Now there what we understood, again, that electron transfer at the metal ligand interface, okay, which played a critical role in analyzing this product distribution process. How it is happening? Now, if you start this in a generic sense, X equal to oxygen and nitrogen, if you look at that this is the S equal to 0 state, that means it cannot react with the triplet oxygen. So it has to have one resonating form where you have an open cell configuration, and then only you could expect that that particular molecule could interact with the molecular oxygen. Now we saw that the nearest excited state, triplet state, which is 700 centimeter inverse roughly for oxygen derivative, whereas 5000 centimeter inverse roughly for the imine derivative. So there is no question of obtaining or assessing or accessing the triplet state in case of the imine derivative. But we believe because of the lower energy between the gap between the triplet and the singlet state, this oxygen derivative could be represented in its resonating form as Ru3, Ru3, O-O- configurations. And if it is so, it can react with molecular oxygen. Now it can react molecular oxygen in different ways. So one of the ways what we could anticipate that it forms the dioxane intermediate followed by OO bond and CC bond breaking gives us the product. Okay, and we could trace the intermediate through mass and through the leveling experiment that oxygen is coming from the air, all sort of things, and theoretically we can establish all these things. But one could argue once you have this this T2G5 configured Ru3 state over here, the standard or the common practice is that oxygen can interact or react over here, and then we can have that superoxide product, and that superoxide can react and also can give us the dioxytane intermediate followed by the product. But somehow theoretically this product did not stabilize. It does mean that this directly goes to the dioxytane without this superoxide intermediate, and also we tried to trap this superoxide intermediate by EPR, we failed to trap it. So all the parameters are in favor of this thing. So what it supports? It supports that the fissile electron transfer at the metal ligand interface can help us to reach to the triplet state. That triplet state could interact with the molecular oxygen and could functionalize the product. And where the imine fragment is there, we cannot reach to that point of triplet state, so therefore oxygen activation cannot take place. So that is the beauty of this sort of ligand system, particularly with the transition metals, where you can have a lot of opportunity to play with the resonating form or the tautomeric form. Now similarly, the sulfur-sulfur bond is one of the important questions to break, and it requires 2 electrons. Right? Now, how this bond could be broken? There are many ways one could think about it, but what we have shown very recently that either via MLCT process, okay, so metal oxidation if you allow to take place under a particular coordination situation, then we could see that metal is getting oxidized and sulfur-sulfur bond is breaking, and eventually we can also have a dimeric system. This is one way to break via the MLCT process, where the necessary electrons for the SS bond cleavage is coming through the metal oxidation step, and that is only possible if your metal can participate in the the charge transfer process at the interface. And also we can show that if you start with the hydride based metal hydride derived metal precursor, then hydride can also allow this thing without any MLCT process. And there we could see this eventual formation of hydrogen, which could be traced by GC also. So what we have shown over here, without going in details, I'm trying to say that sulfur-sulfur bond cleavage, it is one of the important biological process also, could also be undergone either via MLCT process, and if one needs to perform to the MLCT process, then you have to have a particular metal fragment where metal can undergo the electron transfer within itself. That means more than one stable oxidation state of the metal is feasible, need to be feasible over there. But if you do not have a fragment where the metal can stabilize in more than one oxidation state, as in this particular case, because of the pi accepting phosphine and CO, metal could only stabilize in the one particular oxidation state Ru2, then MLCT is not feasible. But by the presence of hydride, it can still undergo the necessary reduction of the SS bond by the oxidation of the H dot to hydrogen, and that hydrogen could also be characterized. Now, if we just keep all these discussions, etc., etc. Now let us go into another example. Now this is a very unique case of beta dicatamine. The beta dicatamine, all of you know, this C beta position is nucleophilic. It can undergo a lot of reactivities already known. But one important point of the beta dicatamine, it is very close to the alpha diamine, say bipyridine. But only difference is bipyridine nodal planes are along the bond. So any redox change could be manifested through the bond parameters or metric parameters. But in case of beta diamine, nodal planes are along the bond. So you cannot judge through the bond parameters. That's why it's called the hidden non-innocence. So you need to have a lot of spectroscopic and magnetic evidences to establish the non-innocent feature of beta dicatamine. Nevertheless, now we thought to look at whether this beta dicatamine could be functionalized or not. Now we got one product, a very simple product with the electron-rich metal fragment, but immediately what happened, the product is formed, product could be characterized, but if you allow it to be exposed to the oxygen, it gets oxygenate and you get the keto function over here. Okay, that could be characterized, etc. Important question is, and this keto is coming from the molecular oxygen, which could be established by the leveling experiment. Important question is, what would be the probable mechanism? Okay, now everything could be followed kinetically, and leveling experiment, etc., etc. Now there are two ways one could think about. Now here it is essentially this carbon functionalizations. This is not oxygen is functioning at the carbon center, and in carbon center you see there is no spin. Spin is over here. Then one option one could think about this triplet oxygen could interact somehow over here, but that is also very unlikely because it is a coordinatively saturated situation. Then oxygen cannot attack over here, but how the reaction takes place. Now if we look at this particular molecule very carefully, we see this is not this Ru3 NAC minus setup. We could see the minority contribution from the resonating form of one electron transfer from here to here. So Ru2 NAC radical system. This is a 20% contribution. So there are two options. One option, if we take this 20% contribution into confidence, then it's simple. One can think about the radical interactions over here through this radical, and we could get the superoxide. Then it is understandable. But the question is, if we follow this thing, some problems are there. Yeah. Now question is, the alternatively one can think about the anionic pathway. Now anionic pathway, how oxygen would attack? There is a report in the literature that crystal field induced triplet to singlet transformation of oxygen. It is known. It is energetically uphill but not impossible. And then you can think about this thing. But in our case, what happened? We could trap this superoxide product, and this is very unique, that carbon-based superoxide, very, very rare in the literature. So you could manage to trap this superoxide, and that could be understood through the EPR spectroscopy. If you look at the G value slide, metal-based anisotropy is there. G value is perfectly fitting with the superoxide. And also look at the spin, 100% spin is over here. Okay, so then the radical role is there. Now the radical route, what we are supposing, based on the fact of the 20% contribution, what we see at this resonating form. Is it true? Whether we are making any mistakes or we are fine. I think we are fine. In order to understand this thing, what we have done, we have made two more compounds using pi acceptor based ligand. Now, if we use the pi acceptor based ligand, say bipyridine, then there is no question of alternative resonating form of ruthenium 3 radical over here, because this will never allow metal to stabilize in the 3 state. So that means here your anionic pathway must be operational, and that justifies the fact that crystal field induced your singlet to triplet to singlet transformation of oxygen, and that oxygen gets linked over here. And that could be also justified by the 65% the HOMO, if you see it, 65% NAC contribution. Probably that helps, and then you get the peroxides and all sort of issues. So theoretically one could explain it. Now, if you just enhance the pi accepting property of the ligand to a certain extent, moving from bipyridine to say azopyridine, we don't see any oxygenation over here. And if you look at this little bit calculation, that HOMO in case of this particular compound, which is being stabilized to a large extent because of the fact of the pi acceptor feature of this ligand, LUMO of oxygen remains intact, and this energy gap enhances to a large extent, and as a matter of fact, no oxygenation takes place. But so far it proves that triplet to singlet transformation of oxygen could be feasible under the impact of the crystal field, and that is what we could see it in case of your bipyridine derived example. We also observed that slight radical component at the C beta site could lead to the oxygenation. If that is correct, then we need to see enhancement of that process by modification of the ligand. So that led us to modify this beta diketaminate to the BHM, that means bis heterocyclic methanide system, which is more electron rich system because of the bridgehead nitrogen. So two varieties we have taken. And if you compare the kinetics of the oxygenation, starting from the parent system, that beta diketaminate or NAC to BHM to the thio derivative, you look at that here, the rate is 10-fold higher compared to the parent one to the thio one as well. Question is why it is so fast over here compared to the other. Now we went back to the calculations. We see in the previous case 20% spin on the C beta position for the parent NAC setup, 20%. When you move to the BHM, the your spin over here 70%. It's completely reversed to 80% spin. And in case of thio case, it is just like the previous situation of the NAC. So therefore, the higher spin accumulation at the C beta side accelerates the oxygen or the oxygenation process, and that could be also very clearly manifested through the EPR spectrum. Here it is mostly metal based, partial spin at the ligand based, but here it is a radical based EPR, so mostly ligand based, no metal component over there. Okay, and then one could easily establish that the radical mechanism is following all the experimental mass, and theoretically we could show that why the sulfur based process is slower compared to the that BHM thing. Everything could be established nicely, Fukui parameters, etc. Resonance hormone, everything is in place. So again, we are trying to emphasize that if we can enhance the spin density, spin at the C beta site, oxygenation rate enhances drastically, 10-fold excess. That also justifies the fact that your whole process is a radical based process. What he proposed in the beginning without understanding much, but through the molecular modifications, we could re-establish that fact, and also we could re-establish the same thing once we move from heavier metals to the lighter metal. So if you go for say copper zinc type of thing with the same BHM, and because of the 70% spin over here, in this case what happened when the radical is formed, the radical recombination process is faster than the oxygenation process. It's a very competitive scenario over here. In case of heavy metal, we could see oxygenation over here, and that is partly because of the coordinatively saturated situations over there. Now here we have taken the coordinatively unsaturated situation, so that there is a competition between radical decombination at this point versus oxygenation. So here we could see the radical decombination, and that again re-emphasizes the fact what we have proposed, that radical based reactivity or functionation. And that radical, how it is being formed? It is being formed through the intramolecular electron transfer. And how it is possible? Because of the redox active ligand. So that is the interesting coincidence between the redox active metal and redox active ligand. Now, if it is so, then he thought to go into the other variants. For example, instead of NAC-NAC, we have gone into, say, ACNAC, oxygen variety and sulfur variety. What we do see, that oxygen variety, there is no oxygenation process. Instead, we see that acetylation over here. And sulfur variety, nothing happened. At the end of the day, this bond got cleaved and you get an unusual compound. That's a separate issue. So the question is that why that oxygen derivative, that is ACNAC, does not undergo any oxygenation. Why only NAC-NAC undergoes, not the sulfur undergoes? So what you could see in case of NAC-NAC, your spin accumulation is around 20%. Now if you go to the sulfur variety, it is 0.17, and if you go to the oxygen variety, it is much less. Okay, so there is an optimum value needed for the oxygenation process, and here the optimum value we could establish is around 20% is necessary. Otherwise, it will not take place, and that is why 0.17 does not work, 0.111 does not work, and it undergoes the acetylation, which could be understood, but which I am not going to discuss over here. And this spin variation, moving from NAC-NAC to ACNAC to SACNAC, could be again manifested through the anisotropic parameters of the EPR very nicely. So what we are again trying to say, that in order to have the oxygenation at the C-beta site, one needs to have a particular or the minimum threshold of spin accumulation. If that does not take place, oxidation won't take place. And also it re-emphasizes the slight variation might lead to have a different kind of reactivity or chemical non-innocence of the substrates over there. But does it mean that under no circumstances that ACNAC would undergo the oxygenation? Fact is not so. Then we moved into 3 isomeric products with the ACNAC, ON, ACNAC. Here what you have used, we have deliberately used the 2 ACNAC, okay, instead of 1 ACNAC in the previous case. And as a result, the 3 isomers are possible. What you could see in one particular isomeric system where your both the nitrogen centers are trans to the acetyl acetonate oxygen, and there we could see one of the rings could get oxygenated. So we are trying to understand why one of the rings, why not 2 of the rings, why this particular isomer is active. One could understand, rather qualitatively, that because of the greater electron density when the nitrogen centers are trans to, both the nitrogens are trans to the ACAC oxygen. In other cases, it is not so. So therefore, that facilitates the transformations, the oxygenation process. Okay, now last 1 or 2 examples. I'll move rather fast. I have, I think, 5 minutes time, I guess, right? Okay. What we have so far tried to convey through a few examples, both at the catalytic site or at the functionalization site, that if you have a redox active setup, I'm talking about metal ligand assembly or compound, you could expect to have fissile electron shuttling at the metal ligand site. If it is so, based on the system, you may have sometimes some additional reactivity at the metal site or mostly at the ligand site. And that quite often happens because of the electron transfer, you can generate a radical at the ligand side, and which makes the ligand rather more reactive. This is one point. Second point is, when we talk about the oxygen activation, in the what we have noticed that the singlet isolated state of the molecule is not active for oxygen, but because of the resonance or tautomerism, what will happen? The excited state comes closer, and then you will have the triplet state, and that triplet state can interact with the oxygen and gives you unusual products, etc., etc., via oxygen activation. Now, if you look at this particular ligand, okay, where do you have the acyclic bridge, right? Now, if you allow the same ligand with the electron-rich metal fragment, very popular fragment for us, and if you allow to react, we get one simple dimeric product where the unperturbed ligand you could see, and along with almost 1:1 ratio, we get the cyclization of this acyclic unit. From this unit, we get the pyrazine unit, and it could be oxidized to the mixed valence state, etc., etc., which I am not going to discuss. What I am trying to mean, how this cyclization takes place. But if you take the electron poor metal fragment like CO, phosphine, etc., then unperturbed product is the exclusive one. What does it mean? That it means very clearly, prima facie, that the electron-rich feature of this particular metal precursor allows the shuttling of electron at the metal-ligand interface, and that enforces that cyclization process. So we try to understand the mechanism, etc., etc. Without going deep inside of that, what we realized that this BPE ligand, what we call it BPE, that means this one, this BPE ligand can stabilize in both the anti and cis form, and there is a cis form is energetically unfavorable in terms of 2.5 kilocalories, something like that. Okay. So the trans form is a thermodynamically favorable conditions, and that's why we get this product, and we could isolate structurally characterize, etc., etc., etc. But the cis form is not the thermodynamically favorable. So as a result, what we believe in, the cis form is the active form in terms of cyclization, and when the cis form is formed, and we have checked it, that this ligand is redox active ligand. You could see the two-step redox active ligand, and then the 2,2,0 could be could undergo the intramolecular electron transfer to give us the resonating form of 3,3,3 diradical. And if this form exists over there, then the radical decombination takes place over here, and we get the CC bond followed by aromatization through the hydrogen productions, and that could be traced by GC. So what I am trying to mean through this, I tried to mean that if you have electronically poor BPE ligand, poor metal fragment, that won't allow to the metal center to shuttle between 2,3 oxidation state. But if you use the electronically rich metal fragment, it allows the metal to shuttle between 2,3, and if metal gets shuttling between the 2 and 3, that enforces the ligand also to shuttle between 0 to radical. So this intramolecular electronic shuttling at the metal ligand interface, by using the redox active ligand, one could think about this sort of cyclization as well, and this is only possible if you have the cis geometry of BPE, and trans geometry if you use, which will never allow you to that kind of cyclization. Am I right? So what we feel again, that energetically I feel that cis orientation, which is active, which forms as a transient intermediate, and through this metal ligand electron shuttling at the interface led to have that cyclization product. Okay, and then one could understand the electron transfer chain, etc., etc., which are very complicated and it may take time. I am not going to talk about this thing. Now, last example, what we'll give it, if we move from acyclic to this aromatic bridge over here, then there is no question of cyclization, pyrazine formation, nothing. And if you react to the same starting material, electron-rich starting material, ACAC, then what will happen? We see that oxygenation at this carbon center, it gives the monoamide formation and then the double amide formation. And carefully look at that in each case, it happens to the metal, this should be the metal in the 2 state. It happens to the metal oxidation. Okay, metal is getting oxidized and amide is forming over here. So when both the site is, an oxygenation takes place at both the site, then both the metals are getting oxidized. I'm sorry, this should be 2. And how it is taking place? It's a bit complicated setup, but we believe in, we have certain evidences in favor of that. We believe in the same phenomena. If you have a redox active ligand, and we know this ligand is a redox active ligand, we know this metal is a redox active ligand, which can shuttle between 2 and 3 state, and the ligand can shuttle between the neutral to the radical to the dianionic state. We don't need the dianionic state, we only need the 1 electron shuttling between these things. So when we put these 2 redox active units together in the form of a metal complex, where it is suitably placed, positions, etc., etc., then this electron transfer takes place over here, forms the radical followed by all sort of things, and then you get these 2 monoamide. Okay, and once this monoamide form, then again the metal ligand electron shuttling takes place at the other available site, and then oxygen interacts and it gives us the amide on the other side. Okay, so it's a beautiful way to portray that how this redox active setup would allow the ligand to activate, ligand to be functionalized, which are otherwise difficult to conceive or even impossible to perform it. And remember, none of the processes are feasible without the involvement of the metal centers. We do not know what would happen with the other metal units. This is the particular metal units we like to explore. And at our hand, what we have noticed that if you want to have this kind of electron shuttling at the metal ligand site, you need to have electronically rich ancillary ligand so that metal can itself shuttle between the at least 2 oxidation state, and of course ligand has to shuttle again 2 or more redox states, and energetically they need to be very compatible so they can share each other thing, and they may allow the chemical non-emissions of the substrate through the metals participation. Okay, so and then complicated electron transfer as it is, I'm not going to discuss this issue, so I should come down to the conclusion slide. So what I have written very clearly, the varying extent of inner sphere electron transfer and valence tautomerism resonance leading to redox-induced chemical non-emissions of substrate. So first of all, we have to use that inner sphere electron transfer and intramolecular electron transfer. Okay, we are not putting any electron inside, we are not taking any electron outside of the system. Whatever the electrons are having, we are allowing the electrons to rearrange within themselves because they are energetically and symmetrically compatible. Okay, and that leads to have the radical imposition at the ligand site, and which allows it to function and to lead to have the ligand or substrate chemical non-innocence over there. So it's a interdependence event. So metal is getting functionalized in terms of its oxidation state, and ligand is getting functionalized in terms of its redox followed by chemical event. So let me put it this way. So the funding and the student, and thank you very much for your kind attention. Thank you.
Thank you, sir, for the nice, wonderful lecture. So I enjoyed a lot. Hope the students are also equally enjoyed the things. Hope to hear from 1 or 2 quick questions from the students.
Sure.
Any questions? I don't find anything from the live chat. So any questions from the faculty colleagues across India? One or two quick questions.
Hello, sir.
Yes.
Yeah, this is very nice talk, I must say, and very well thorough chemistry and everything. One question is coming to my mind, that why ruthenium has some special effect, or what exactly, why this kind of system, non-innocent ligand with ruthenium, they provide the radical kind of system, or they stabilize, but with other metals usually it is not observed. Yeah, of course, some other metal ions also they do stabilize but with ruthenium it is quite common. So is there any special like some properties related with the ruthenium metal ion?
Yeah, there are two ways to answer it. First of all, being the heavier metal, it can stabilize easily in variable oxidation states. Okay, for example, if you take the lower case iron could also be stabilized in the 2 and 3, but what happened, the iron spin state gets changed very easily, and that makes the system quite complicated in terms of understanding. But ruthenium case, one particular thing, you can make it silent, the spin configuration. It would always remain low spin first. And in both the 2 and 3, they are equally stable. And it can also go to the 4 without much difficulty. So there's facile electron transfer between 2, 3 and 4 of ruthenium, which is not always true for iron. And the always the low spin configuration of ruthenium, which makes the thing much more easier to perform this kind of chemistry or this kind of physical features. If you go to osmium, if you go to next element osmium, you will have almost the similar behavior, but not as good as ruthenium, because ruthenium is the perfect fitting, which is the in between iron and osmium. Is the perfect fitting. Osmium, what will happen? It will take place. It will follow more or less like ruthenium, but the electron transfer is rather sluggish in case of osmium compared to ruthenium. And in iron case, it is rather fast. And iron case spin gets changed too fast along with the electron transfer process. So ruthenium case, you can naturally it is being fixed up over there. So everything fits quite nicely in order to understand the redox feature. So ruthenium is the best candidate to understand the redox based items. This is how I feel it.
Thank you very much. Yeah.
Any other questions? Yeah, there is a live chat. There is some issue, but anyway, they will fix it shortly.
Yeah, their slides have got.
Yeah, that is some issue. Okay.
Some internet issue is there.
Yeah, thank you, sir, for the wonderful lecture.
Okay, thank you.
Yeah, if no question, kindly join along with me in thanking Professor Gautam Kumar Lairi for the wonderful lecture. And on behalf of the organizing committee, I thank you once again, sir. Thank you very much.
Thanks, Sini.
Okay, sir. Bye.
Bye.
Yeah. Yeah, now we will move on to the next lecture, the second lecture. The second speaker of this symposium is Professor Rupam Dinda. Professor Dinda did his PhD from IICS Kolkata, like Professor Lairi. He was a postdoctoral fellow at Missouri University, United States, and the University of Heidelberg, Germany. Soon after his postdoctoral research, he joined as an assistant professor at NIT Rourkela in 2007. Since 2018, he is currently he is a full professor at NIT Rourkela. Professor Dinda received Professor Dayanidhi Patnaik Memorial Award from Orissa Chemical Society in 2021. He published over 600 research articles. His research is mainly focused on the pharmacological, catalytic, and magnetic chemistry of a wide range of transition metals. both in artificial and biological settings. With this brief introduction, may I now invite Professor Rupam Dinda to deliver a lecture on exploring the solution behavior and the biological potential of transition metal complex. Professor Dinda, please. The floor is yours. Yes, yeah.
Am I audible? Sir, am I audible?
Yes, yeah, you can share your slides.
So I already have shared my slide. Can you see my slide?
Yes, yeah, now it is. Yeah, can you go to the full screen mode?
Yes.
Yes, fine.
Okay, okay.
Yes.
So thank you, Professor Srinivasan, for nice introductions. And good evening, one and all present in this virtual meeting today. And I would like to give my sincere thanks to the organizer, especially Dr. Patro, giving the opportunity to talk on this virtual meeting. And also congratulations to organize such a good workshop with a huge response of a large number of student participants. So, and it is a always challenge and honor for me to talk immediately after talk of Professor Laidi, and from whom we always, like from our PhD times, so we are learning the interesting redox chemistry linked to the synthetic inorganic chemistry. So the topic of my today's talk is exploring the solution behavior and biological potential of transition metal complexes. So I have divided my talk into three different outline. So the first segment of my talk would be that in comparison to the study of biological applications of well-known oxide of vanadium 4-5 systems, especially the chemistry of non-oxide of vanadium complexes, and in relation to their biological activity has not that much explored. And also for a particular system, the solid state chemistry may be different from that which is generated in the solutions. In the solutions, a compound which may be stabilized in the mononuclear state, structurally characterized, but gradually transformed to a new species through formation of dimeric, polymeric species, through oligomerization, hydrogen bond formations, or redox reactions. So next segment of my talk would be the transition metal mediated organic transformations has received a lot of attentions. So a lot of chemistry has been developed where transition metals took a role for the facile the organic transformations, but particularly molybdenum complexes, especially organometallic complexes, as a metal source used for this type of transformation is comparatively rare. And another segment of my talk would be also there are many metal complexes exhibited though good biological activities, but their water solubility is very much challenging, very much unsatisfactory. Though there are several papers published where people claim that transition metal complexes as a potential metallo drugs, but their solubility issue is very much threatening. So that is another segment. And the last one is like the biological applications of platinum group metals, especially the ruthenium metal complexes. And as we all know, maybe there are four number of ruthenium metal complexes, transition metal complexes as a drugs are under clinical trial as anti-cancer therapeutics. And one of them may be in this slide, like NAMI1, which has already completed the phase 1 clinical trials. So the first segment, that chemistry of non-oxide metal vanadium 4 complexes. So for the student's perspective, the non-oxido means the species that which has got no oxo bond, especially the oxido metal complexes, vanadium and molybdenum. They always have a tendency to go to their corresponding higher oxidation state containing a metal oxo bond due to very much oxophilic in nature, like oxide of vanadium 4, oxide of vanadium 5 in the 4-5 oxidation state, as well as for molybdenum dioxide of molybdenum 6. So it is a challenge for the researchers to break this strong metal oxo bond like vanadium oxo, molybdenum oxo bond. And when the metal pickers are itself used as a species which has got the metal oxo bond itself. So during our journey, we have developed a couple of rare non-oxide of vanadium 4 systems in our laboratory, and maybe for the first time in the literatures, to the best of our knowledge, where the rare and very unstable non-oxide of vanadium 4 systems, we could able to use them to study their biological assays. So this is the methodology by which we could isolate 3 different non-oxide of vanadium 4 species by introducing some sterically hindered ligand. And during their characterizations, so we observed that, which is quite unusual for this type of systems, where the systems are found very much stable in the normal atmospheric conditions as well as even in the solutions. And because of that, for the first time in the literature, we could able to use any non-oxide of vanadium 4 species to study their biological activity. Like here, we have studied their in vitro insulin limiting and as well as anti-cancer activity. So before we studied their activity, it was a challenge to have them stabilize in the solution. So and as a part of routine study, we have studied their solution phase stability with the help of spectroscopy, UVs and EPR with time-dependent manners. But it was not possible, and also it was not the focus of that time, that what is the actual species or the key species which is generated in the solutions. It was not possible to develop in that particular work. And with a comment we received from the reviewer, very recently we have developed a couple of new systems which are even again non-oxide of vanadium 4 we could able to stabilize with the appropriate ligand environment. And here in this case, we are ended with our new ligand environment. We are ended with 2 of the non-oxide of vanadium 4 as well as one of the oxo alkoxo vanadium 5 species. And in this particular case, we could able to characterize their solution phase stability or the biospeciation. Actually, what is the species which is gradually transformed or present in the, especially in the aqueous medium, and which is very important to study or claim any species as a drug for cytotoxic activity. So we have studied their solution phase stability in terms of spectroscopic techniques, especially here high resolution mass spectrometry helped us to study the species which is actually generated. And we have observed that for the case of non-oxide of vanadium 4 species, which are supposed to be very much unstable, but we found them again, like our previous work, quite rather stable, and few of the compound, not all, gradually transform to the corresponding oxide of vanadium 4 species. And so this is the peak of the corresponding non-oxide of vanadium 4, which is isolated in the solid state, structurally characterized, and in the aqueous medium, gradually transformed to the oxo vanadium 4 species. This is the ligand fragment. Whereas in case of the other component, that is the oxo alkoxo 5, which was also isolated, structurally characterized, that compound gradually, completely, 100% transformed to the corresponding dioxide of vanadium 5 species, and only one of the molecular ion peak of the corresponding changed species is detected in the solutions. So with the knowledge that what is the actual species now present in the solutions, and so with the help of mass spectrometry, we also have further evaluated as especially the non-oxo 4 systems, and in the EPR spectroscopy, and in normal DCM at 77K as well as in aqueous media. And also from the observation, it is clearly observed that in aqueous media, the non-oxide compounds gradually, some of the portions gradually transform to the corresponding oxo vanadium 4 species. So now we have used the systems to study their in vitro cytotoxic activity against ovarian cancer cell line A2780 and prostate cancer PC3. And also we compared our results with normal cells P79s. And here from the results, you can see it is observed that our compounds are very much cell-specific against ovarian cancer cell. And interestingly, some of the ligands, especially ligand 1 and 2, also showed significant activity in terms of killing the cancer cell as compared to the complex. And from the cell specificity and selectivity index study, it is observed that though the ligand shows equal activity or good activity, but the corresponding complex was more toxic toward the cancer cell lines. So before we study their cytotoxic activity, we also have studied their possible interactions with, here we have studied through docking approaches the interaction study with two model proteins. One is lysozyme and another ubiquitins. And here, the species which is generated in the solutions, few of the species covalently bonded successfully, and few of the species which is generated, they are found non-covalently bonded to the two proteins we have used. So now another set of works. So that is like according to my title, the study of solutions phase stability. So that is the important parameters or the key factors which from the last few quite large number of articles or systems we have developed in our laboratory, where we could able to successfully study their solution phase stability. So like with this diagram, represented diagram. So with the example, like suppose you have a vanadium 5 systems, oxo, alkoxo with a ligand environments. So that is maybe isolated in the solid state, structurally characterized. But that may not be the same in the solutions. Whenever we have dissolved this in normal laboratory solvents, in normal atmospheric condition with presence of oxygens, those species gradually could transform to the corresponding oxo-bridge divanadium species. And that species actually hold the possibility of metal precursor to generate the corresponding mixed oxidation vanadium 4 spice species through electrochemical reductions or single electrochemical reductions to give the corresponding very unstable and very rare mixed oxidation 4-5 species. And also if you reduce by 2 electrons, you could able to get them the stabilized to corresponding reduced 2 electron reduced di4 species, and that species make gradually break down to transform to the corresponding mononuclear vanadium 4 species. So couple of systems we have developed in our laboratory, and so with a shortage of time, I'll show you few of our recent, few of our very interesting work. So in this particular work, with simply changing the reaction conditions, we could able to isolate and stabilize the corresponding oxo, non-oxo, monomer, dimer, and we also observed their changes in the solutions gradually. Suppose so with this ligand environment, with simply using ethanol, we could able to get the corresponding oxo-alkoxo, whereas by changing the solvent and with the inert atmosphere, we could able to stabilize their non-oxide or rare and stable species. Now this species, alkoxo, oxo species, whenever we simply dissolve during the course of spectroscopic characterization in the lab, any laboratory solvents, so like acetonitrile, dichloromethane, they gradually could transform to the corresponding oxo-bridge dinuclear species, and that species actually hold the possible metal precursor to generate the corresponding reduced species through chronocoulometric reductions. And in this particular case, we could able to reduce them, but it was not possible to trap the mixed oxidation 4-5 species. Rather, we are ended with mononuclear vanadium 4 species. Maybe the intermediate was the dinuclear 4 fast by 2 electron reductions, and those gradually break down to form the corresponding mononuclear 4 species, and which is characterized isolated in the solution state. It was not possible to trap them in the solid state, and is nicely characterized with the help of EPR, and the EPR of typical vanadium 4 has been trapped. So now immediately in the same year, we could able to characterize the corresponding mixed oxidation 4-5 species by simply tuning the ligand environment. And here also similarly, gradually the species which was in the solid state transformed to a new oxo divanadium species in the solution, and that species we used as a metal precursor as a source to generate the mixed oxidation 4-5 species through electrochemical reductions. And here in this case, we could able to trap the mixed oxidation 4-5 species in the solution, and that is characterized again with the help of EPR, and which shows the typical characteristics, room temperature 15 line EPR for that generation of mixed oxidation vanadium 4-5 nucleus. And the generation or transformation of this monomer to dimer or solution stage stability or transformations also being tracked with the help of redox study using cyclic voltammetry. And if you have a close look, you see the redox with dotted line at the very left, it actually represents the corresponding redox of the mononuclear species. And when we simply leave the sample for a longer period, say 1 hour, untouched, and we record their cyclic voltammetry and voltammograms, you see the voltammogram now shifted towards negative vertex, and the new redox, whatever it is observed, that is actually the representative redox of the corresponding oxo-bridge dimer, which is actually with a time generated in the solutions, and that redox nicely resembles or correlated in the same region of a already earlier work where we published a dinuclear oxobridge dimeric species, and from there we can conclude that with the redox study also we could able to trap the transformation of a species in the solutions. So time to time we have developed new ligand systems. So in this set of work very recently we published where instead of tridentate aryl agenes, we have incorporated some reduced saline ligand, salan, and here also we could able to trap the corresponding monomer, dimer, and also we could study their inter-transformation from monomer to dimer in the solution. And for the students perspective who are present over here, the master student and PhD students, you would be happy to see with the help of NMR, nicely we could able to see their transformation in the solutions in proton and as well as vanadium 50 on NMR. So you see, this is the species actually in the monomeric vanadium oxo 4 in the backbone of the simple saline ligand with 4 coordination environment, and that was actually in the solid state structurally characterized. But whenever we studied their NMR in solution, simple NMR solvent, instead of getting the actual peak, we have observed a lot of peak, a species of mixture compound, or maybe the 2 species generated, and that is actually observed in the proton as well as in the P50 and also 2 nucleus. Rather, we supposed to get a 1 nucleus vanadium. And again, whenever we have added few drops of methanol in the same NMR tube and we have re-recorded the NMR, you see gradually the NMR cleaned up and we got the corresponding peak of the corresponding monomer in the proton as well as in the vanadium 51 NMR, the dinuclear species which was present initially with the addition of methanol that could easily transform to the single nucleus vanadium 5 species. And that actually the systems or these transformations can be explained with this equilibrium, and actually the mononuclear species in presence of water as an impurity in the normally present in any commercially available NMR solvent facile, the transformation of this monomer to the corresponding oxobridge dimer by the release of that methoxide group which was bonded to the vanadium from the source of solvent, now released as a methanol. Now if you add the external few drops of methanol on it, so now the equilibrium may be shifted and should be shifted to the left and to maintain the equilibrium, and gradually your compound, whichever is the new species, dinuclear species generated, so that could be shifted whole to the monomer, and that is actually being trapped in the proton and B50 on NMR spectrum. So after knowing the actual species which is there in the solution, we also have used them for the study of their cytotoxic activity. Here in this particular case, we have used our system to study their cytotoxicity against MCF7 and H229s, and here in both cases compounds are equally active to show the cytotoxic activity, and before we do the cytotoxic activity we have also equally evaluated their interactions with proteins and DNA. So now the next segment of my work, whatever I have mentioned in my outline of the talk, like though there are a lot of work developed nowadays and people claim that tensor metal complexes as a metallo drugs, but their problem in the solubility in aqueous medium shows some difficulty, and it is a challenge for the researcher to isolate or to develop some targeted synthesis by which they can stable their compound in aqueous media or physiological pH mediums, and which is important to claim a system to be active towards like drug activity or clinical trials access. So now in our lab, after several effort, we could able to trap few of the systems in our lab during our journey of oxo vanadium systems, where we develop some systems which are very much stable and soluble in aqueous media, and we studied their hydrophobicity characters. And in this particular set of work, we have seen that our compounds, which is stable in the aqueous medium, showed some cell-selective anti-cancer potentials with some specific cancer cell lines we have studied. So earlier in 2014, we have observed that we have developed a series of compounds of dioxide of vanadium 4 species with some alkali metal cations as a counter ions, and this is the one of the representative compounds structurally solved. And we have seen that those compounds are highly stable in water, and for that behavior we have studied their biomolecular interaction study as well as the cytotoxic activity. And so from this result we observed that in case of 2 particular compounds, compound 6 and 7, which has got their ligand backbone attached with some heteronuclear aromatic units shows the higher site of cytotoxic activity or as well as the binding and cleavage activity. And from this result in hand, with that with that knowledge, we recently have developed with a targeted synthesis. We designed some new molecules purposefully introducing some furan and pyridine ligand fragment in the ligand backbones. And here also we could able to stabilize 5 different water-soluble dioxide of vanadium 5 species, and this is one of the representative structures of the species isolated and stabilized. And here we have successfulully characterized them in the aqueous medium. This is the time-dependent NMR in D2O as well as time-dependent UVB absorbance in water mediums. And not only that, with spectrometry, also with high-resolution mass spectrometry, we could able to trace them in the ESI mass spectrum, their stability, and finally we have used them for the study of their cytotoxic activity, in vitro cytotoxicity. And here we have used several cancer cell lines, and as well as also we compared with normal cell lines. And if you have a close look, you see in case of with the study of 3 different cancer cell lines, particularly in HT29s, we have observed very high activity for all the complexes we have observed. And to establish this as a cell specific towards this particular cancer cell lines, we have also evaluated their wound healing assay. And from this wound healing assay, it is observed that particularly against HT29s, where very strong inhibitory cell migrations of the compounds has been observed. And also to correlate that there is any role of the hydrophobicity character of the compounds with the cytotoxicity, we have evaluated their hydrophobicity with partition coefficient experiment, and it is observed that optimum level of hydrophobicity is required to claim a compound to be a quite good cytotoxics in that series. So now not only the mononuclear oxide of vanadium 4 and 5, we have developed some corresponding dinuclear 4 systems in our laboratory during the journey, and we also use them to study their biological activity. And here, by introducing some aryl azo ligands, we have developed some ethoxide bridged, some unsymmetrical twisted divanadium 4 species with a unpaired electrons in the both the vanadium 4 centers. And due to having that unpaired 2 electrons in the 2 vanadium systems, we have studied their temperature dependent susceptibility, and that was actually not the focus of this today's talk. That's why I skipped that part. But we also have used them for the study of their biological activities, especially the cytotoxic activity against 2 cancer cell lines, HeLa as well as HT29s. And here also we have seen that our compounds was very much specifics in a particular cell lines, here HeLa cell lines. And before we studied or used them their biological activity, in a routine study, we have studied their solution phase stability with the help of time-dependent UVB studies. So not only the vanadium systems, so as a part of our work as oxometal complexes in our lab as a metallodrugs, we have also developed a couple of variable valence molybdenum like 6,5 systems as a potential metallodrug, and especially we have studied their transformation or so-called chemical transformations or speciations with the time in a solution, especially in the aqueous medium. And we see that a couple of years back we have developed a systems here. We have so not only their biological assays, we have observed also a very interesting unprecedented molybdenum-assisted CN bond cleavage is observed, particularly in a case of cellophane ligands. Here, if you follow this methodology, so particularly the path A, path B with the same reaction condition, same metal precursor as the source of metal, but simply tuning the ligand first series is with a aromatic phenylenediamine as a amine backbone of the salen, and whereas in the second set aliphatic amine as a amine backbone. Now, in a case of aromatic amine backbone, you see instead of getting a normal expected mononuclear molybdenum 6, what we have got in case of aliphatic amine set of ligands, and that is quite usual and well known in the literature. But in this case of paraphenylene diamines, where we have seen that compounds that corresponding dimolybdenum 5 species with a rearranged and broken ligands, is attached with a metal-metal bond. So that particular transformations we have successfully established with a proposed mechanism, and during the course of the study of the reactions or find out the mechanism, we have observed that actually the aromatic amine backbone containing ligands, they gradually transform to a species with a metal-metal bond, and dimolybdenum 5 species, actually it was passed through an intermediate which is very, very unstable single electron containing molybdenum mononuclear 5 species, and it was very difficult to isolate them because of their very instability in the normal atmospheric condition, but we could able to trace them in the solution phase with the EPR, and this is the typical EPR of molybdenum 95 and 97 nuclei. Here with a time dependent EPR in DMSO solution at room temperatures, we have seen that the species, actually the intermediate species which was having a unpaired single electron containing mononuclear species, gradually transform to the corresponding dimeric divanadium 5 species, and where the two of the monomer with having a single electron, they actually gradually antipyrimagnetic coupling to each other, and they transform to a dimagnetic dimolybdenum 5 species, which is rather stable in the atmospheric conditions. And that is actually observed in the course of EPR. If you see with a time scale EPR with a time of like initial at the time of 7 minutes, then 14 minutes, the B and C is 20 minutes, and the D is 26 minutes. You see gradually from A to D, the EPR gradually collapsed down to from a paramagnetic to diamagnetic species, and the fast EPR represent the 6 hyperfine lines of the typical coupling between the unpaired electrons present with the molybdenum 95 and 97 nuclei, and gradually due to antipyrimagnetic coupling of the two unpaired electrons and to form a metal-metal bond, that collapse down to a diamagnetic species, and that is actually isolated and structurally characterized. So we propose the mechanistic pathway by which we claim that it is a molybdenum assisted reactions. So this is followed by this pathway where in presence of water, we initially got an intermediate of CN bond cleavage, and ultimately through the subsequent reactions and breakdown of the fragment of the ligand and comproportion reactions, we are ended with a mononuclear with a single electron molybdenum 5 species, and then they dimerize to transform to a stable dimolybdenum 5 with a metal-metal bond. And to establish them as a molybdenum assisted, we have also examined the reactions with the same ligand environment with a aromatic diamines amines with similar metal precursor like uranium, vanadium acetyl acetonate, but in those cases there was no case of any rearrangement or any formation of metal-metal bond formations or ligand rearrangement. Simply they could transform to the corresponding mononuclear vanadium oxo 4 species. And also to establish this is a ligand specific of having a role of aromatic diamine in this particular case. So we could explain this in a way that this intermediate, that IA, which is actually during the course of reaction it is generated. So that would definitely, in case of aliphatic amine, so the intermediate which has got a anionic like iminium ion is generated, that would not get any resonance stability whenever you have the aliphatic amine as a backbone present. That's why this is the ligand specific, and this particular transformations has been observed in case of the ligand which is having this aromatic amine as a ligand backbone. So now not only that species, we have also very recently able to synthesize a series of mononuclear and dinuclear molybdenum 6 complexes, and we could isolate them in the solid state and structurally characterize. But interesting fact is that whenever before we use them for the study of their biological activity, so we studied their solution space stability, or we wanted to see is there any speciation or any fate of the what is the actual fate of the systems, and we have seen that those compounds do not retain their actual structure in the solution, rather they transform to a new species. This is the structure which was in the solid state, the molybdenum 6 coordinated with the ligand, and also one of the coordination is occupied by the solvent. We have used methanol, ethanol, and here the bridging ligands we have used to trap two of the monomer to bridge them to a dimeric species. But whenever we dissolve them in the solutions, they actually, all the species gradually transform to the corresponding dioxide of 5 coordinated species, and this is the optimized DFT structures. The spectroscopic techniques help us, or characterization help us to establish the species which is generated in the solutions. And finally, the high resolution mass spectrometry help us to detect the actual species, and it is observed that the monomer containing the solvents is gradually release the solvent molecules from their coordinations and transform to the corresponding 5 coordinated molybdenum 6 species, and the dimeric species also release the bridging 4-port bipolar ligands, and also 2 moles of the monomer gradually generated in the solutions. And after knowing the actual compositions of the solutions, so it was very much easy for us to explain our observed biological activity. So during the journey of the biological assays, we have studied their interactions with proteins, with normal techniques, spectroscopic techniques, and with docking approaches also, as well as their interaction with DNA with spectroscopic techniques. And finally, we have studied their cytotoxic activity against a couple of cell lines, normal as well as cancer cell lines. And here you see from the results are for all both the cases, like they are not that much cell specific in both the cancer cells, almost having similar activity, but particularly the case of 3 and 4, which was actually dimeric species in the solid state, as they are generating the corresponding 2 moles of the monomer, and that may be the reason for that particular cases we got the enhanced cytotoxic activity against both the cancer cell lines we have used for this study. So this is the apoptotic studies we performed during the course of biological assays, and from the nuclear standing assay, it was clearly observed from the morphological changes that there was a the drugs were effective to kill the cancer cell. To further evaluate, we have studied their cell cycle analysis and cell apoptosis study, and from the results, it is clearly observed that the compounds were sufficient to kill the cancer cell with the apoptotic pathway. So now, at the very last stage of my the overall work, that is, so during our journey, not only the oxidometal systems, we have developed some system with platinum group metals, especially the ruthenium systems as a metallo drugs. And as I have already mentioned, a couple of systems already are in clinical trial. There are more than 4 systems of ruthenium as a transition metal anti-cancer drug. And so here, very interestingly, very recently, we have observed the systems where not only their biological relevance, interesting chemistry of like the CO generation during the course of reactions by metal assisted alcohol dehydrogenations of the solvents. We have used the alcohols using 2-aryl as a ligand fragments, and we probe that generation of CO with labeling experiment in our work. And from the outline, you can see, so whenever we using this aryl phenols as a ligand backbone in the similar reaction conditions, so in case of ruthenium, in a ethanol, you can see there was no source of CO in our reaction conditions, but in the final product, we got CO is coordinated. So with a reason to find out what was the actual source of CO, so we have observed that during the course of reactions, actually ruthenium assisted the dehydrogenations of the alcohol, ethanol we have used, and gradually we get the CO generated in the solution. Ultimately, it is coordinated to the ruthenium center. And to find out or to establish this is a solvent assisted CO generations, we have used another solvent like acetonitrile. But in case of acetonitrile, there was not the case. Rather, we are ended with acetonitrile coordinated ruthenium species, which is quite usual for ruthenium chemistry. And to also further establish this is actually a metal assisted reactions, we have also studied with iridium systems with metal precursor in the similar reaction conditions, even using the same solvent ethanol. But that was not the case here. Rather, we are ended with simply iridium 3 species having no CO generation and no dehydrogenation of the alcohol. So we proposed a mechanistic pathway for this metal assisted alcohol dehydrogenations, and all the steps are well supported by the chemistry for the master students and PhD students over here. The chemistry is a very well known textbook chemistry like beta hydride eliminations, then coordinations, then oxidative addition, reductive elimination, migratory exclusions, and finally the CO coordination to the metal centers. And now to compare whether it is metal specifics in case of iridium, simply the transformation that through the oxidative addition of the ligand and CH activations, we are ended with very stable iridium 3 species, which quite usual for iridium to gain the 18 electron configurations, whereas in case of ruthenium, intermediate compounds, this B species actual unstable species, rather it was requiring to get stability of further reactions. So that's why in case of acetonityls, the unstable species get bonded with acetonityl and stabilized with 18 electron stabilized species. But in case of ethanol, that systems facile these catalyzed reactions of CO generations, and ultimately finally CO is generated and that is bonded, and finally it is stabilized the species with 18 electron configurations, which was in the intermediate as an unstable species. Now so this is the actual solid state structure. You can see this is the CO bonded to the ruthenium with a reaction in ethanol, and this is the acetonityl bonded in acetonityl medium. This is the iridium with hydride, no CO in the similar reaction conditions. Now to establish this as a CO was the actual source of alcohol, we labeled experiments we have performed with a radioactive C13 level ethanol we have used, and nicely we have trapped the product where the C13 level CO is coordinated to the ruthenium with IR. And you know, for the students who are present in this forum, you can see from the Hooke's law, you know, the wave number is inversely proportional to the reduced mass, and if you have a labeled isotopes, so you should expect the increased reduced mass, and that is actually reflected with the observed IR spectrum. So the peak of level CO, the peak of CO stretching is shifted towards lower wavelength because of this Hooke's law. And also we have trapped our species with the high resolution mass spectrometry. You see this is the mass of the corresponding C13 labeled CO with a 1 unit increased mass as compared to the normal CO coordinated species. And not only the experimental result, we have evaluated or we simulated the peak and we got the similar results. And as our actual objective to use them to study their anti-cancer activity. And here also we have used 2 cancer cell lines, particularly HeLa and H229. But for this particular case, we see even with respect to the source of metal, which is there present in the ligand environment, compounds are showing comparable cytotoxic activity in all the cases. So now for the student perspective, I thought to give you some view of the journey of the lab we have developed, funded by DBT in my institute, in my group. This is the cell culture lab. So these are the common apparatus commercially available for one-time use for cell cycle analysis or cell culture study. This is the CO2 incubator required to stabilize or protect your cell in a proper environment of physiological pH conditions by constant passing of CO2 gas with a certain temperatures. So this is the biosafety cabinets to do all biological manipulations and with the facility of UV light source to avoid some contaminations if there is any during the course of study. So this is the image of some microscopic image of the normal cell, what we have we generally purchased from NCCS Pune for the cell source, and several cancer cell lines and normal cell lines what we generally used in our lab. And this is the actual cell passaging procedures in our lab. We do by our own to clean up the cell and to protect the cells for overgrowth or to avoid the contaminations with media, in presence of media. And this is the MTT assay, the step of gradual MTT assay of the cytotoxic activity, step by step. And this is the image of the final plate of MTT assay, where you can see the presence of some active cell and also some the cell which are already killed by the application of the drug. And finally, this is the step where you can easily find out the morphological changes with the use of some DAPI or any other scanning to see the actual image with the high resolution confocal laser scanning microscope facility for cell imaging study in our institute we have developed, and by which you can see whether your cell is enough to kill the cancer cell or not, or other tumor cells. So I would like to acknowledge my work, the funding agencies who funded my work, and also my collaborator who time to time help me for the study. What we don't have the facility like EPR, magnetic susceptibility, we don't have the facility in my institute. We generally collaborate. And so these are the some of our recent work shared by the Inorganic Chemistry in their official Twitter handle, and also our work recognized by Odisha Chemical Society this year. And ultimately, the credit goes to the students who actually done the synthesis or biological assay. So thank you all for the kind attentions, and my talk is open for discussion.
Yeah, thank you, Professor Rinda, for the nice lecture. We have one or two quick questions.
Yes, sir.
Yes.
I'm ready. Is there any questions?
I'm looking at the chat box. So far, I have not seen anything. Yes. Any questions from colleagues?
May I ask one?
Yeah, please go ahead. Yes.
Hi, Professor Dinda is Apurva from ISR Bhopal. So I was looking at the cytotoxicity data, and they're like in the micromolar to millimolar range. So is there any possibility to make them even more sensitive to where we can kill in nanomolar concentration? So is there any tuning that we can do in the metal complexes that can make them even more cytotoxic?
So very nice question and important questions. So that may be challenging for us, but till now we have not thought in that way. But whatever the concentrations we have used, and we observe their results in the concentration level, whatever we have reported. But obviously, so we will try, and so thanks for your suggestions. But till now, we don't have any results to claim our systems in nanomolar level of like their concentrations, which is effective towards killing the cancer cell.
Okay. Another thing on the same line, I have observed when you have done the cytotoxicity, immediately after when you are adding like 5 micromolar concentration, you have a really high reduction in the cytocell viability.
Okay, like and that was actually carried out during the lockdown period, so it was not possible to rectify. But in other work, we have seen that even like lower down the concentrations, so it was able to establish our drug towards sufficient activity in terms of their cytotoxic activity.
Can I have one more? Can I ask one more?
One last question.
Okay. I see some selectivity also you got over some cell lines like ovarian cancer cells. I think you have mentioned in the beginning. So why you have selectivity in certain cell lines compared to the other?
The reason?
Yeah, the reason behind, like, is there any specific pathways they're targeting to kill only the ovarian cancer cells? Over?
No, specifically not for that particular work, but recently with the questions we received from the reviewer, we have carried out some cell cycle analysis, cellular uptake study, and annexin B. But that the work what you referred, so it was not done. It was not possible. So we haven't checked that what was actually the reason behind this, like cell specificity or the any mechanistic pathway which was involved. But nowadays, a lot of questions people are asking. So it is a challenge for us to further like to establish what is the actual reason behind this. So we are in process to develop new systems, and also to establish whether we could actually mention the reason behind this of cell specificity or cell selectivity.
Okay, thank you very much. Thank you very much.
Yeah, we are running short of time, we will move on to the next lecture. If there is no question, kindly join along with me in thanking Professor Dinda for the wonderful lecture. And on behalf of the organizing committee, I thank you once again for the wonderful lecture. Yes.
Thank you, Professor Dinda.
Yes. Yes. Yeah. We will move on to the next lecture. Dr. Sheikh Mobin. Yeah, he is sharing his slides. In the meantime, we will introduce him. Dr. Sheikh accomplished his bachelor's and master degree from Wilson College, University of Mumbai. And also he did his PhD from Mumbai University. In 2012, he joined at IIT Indore, and presently he is working as an associate professor at IIT Indore. And his research interest includes optical and electrochemical sensing, solid state structural reactivity, metal organic frameworks based supercapacitors for energy storage, catalysis, sensing, and biomedical applications, design and synthesis of greener C dots, carbon dots, and their wide range of bioimaging and biosensing applications, and also involved in design and synthesis of small molecules as cellular organelles, target and cell imaging. And some of his achievements are: he is a fellow of Royal Society of Chemistry, that is FRSC, fellow of Indian Chemical Society, fellow of Maharashtra Academy of Sciences, and also a recipient of Material Research Research Society, that is MRSA medal in 2021. And he is also been named as a golden author by Dalton Transactions. With this brief introduction, may I now invite Dr. Sheikh Mobin to deliver a talk on simultaneous one-part synthesis of iron-doped carbon dots and Fe3O for nanoparticles and heteroatom-doped carbon dots as label-free fluorescent probe for sensing and light-induced bacterial inactivation. Yeah. Professor Sheikh Mobin.
Yeah. Yeah, thank you so much, Professor.
Yes, yeah, please go ahead.
Seeing you after a long time.
Yes, yes.
Thank you so much, Dr. Srikanta, for giving this opportunity, and other organizing committee for advances in inorganic chemistry, recent advances from IIT Bhubaneswar. So I hope I am audible and my slides are visible to you.
Yes, please go ahead. No problem. Okay,
thanks. Yeah. So I'll be talking about two different cases here. One is simultaneous one-part synthesis of iron-doped carbon dots and Fe3O4 nanoparticles, and the other one is a heteroatom-doped carbon dot as both as a label-free fluorescent probe for sensing and light-induced bacterial inactivation. So for the younger audience. Yeah, for the younger audience, just wanted to brush up what is carbon dots and how it came into existence. So carbon dots were discovered accidentally in 2004 at the time of purification of single wall carbon nanotube by Zhu et al. And then later on, 2 years later, Sun et al. In 2006 synthesized a stable photoluminescent carbon nanoparticles of different sizes and named them as carbon quantum dots. And then since then, there are a variety of synthesis routes have been developed, and huge number of reports have been reported, in the literature for where you can see the preparation of carbon dots and for their various properties and applications were reported. So this is the overall approach for developing the carbon dots. Like either you can go by bottom-up approach or you can go to top-down approach to synthesize carbon dots in the laboratory scale. And these are some examples. The best way, the so far reported, the more facile method is the hydrothermal method, through which you can actually generate carbon dots, and it could be a very good stable carbon dots can be prepared in a very facile manner by using hydrothermal method. So there are some other methods are also available, but that requires high heating and pressure, etc. But if you talk about the facile method, hydrothermal is the very widely used and most acceptable for their economically viable purpose. Okay. So we know the carbon dots have a huge advantages in terms of high solubility, low toxicity, environmental friendliness, low cost, and simple synthetic routes. And in addition to this, the surface passivation and functionalization of carbon quantum dots allow additional control of their photophysical properties as well. And since their discovery, carbon dots have found many applications in fields varying completely from chemical sensing, theranostic as biosensing, bioimaging, nanomedicines as drug discovery agents, then photocatalysis and electrocatalysis. But we primarily focus on the sensing, theranostic, and environmental applications of these carbon dots in our group here at IIT Indore. So keeping this in mind, we have proposed, I'll take up two different cases here based on the carbon dots, what we have prepared in our laboratory. So the case one is the in situ synthesis of Fe doped carbon dots and iron oxide nanoparticles. So in one go, we could able to get two different kinds of products here. So hydrothermal methodology, perhaps you know that's the most promising method in recent years for the synthesis of carbon dots, and due to their non-toxic, environmental friendly, and low cost and easy operational techniques. So same was utilized by us also for the synthesis of this carbon dot. So firstly, what we did, we have taken ferrous chloride and was dissolved in some deionized water, and in other solution 1 gram of citric acid was dissolved in 15 ml around 15 ml of deionized water. So both the solution were mixed and sonicated for 10 minutes, and if you see into which 8 ml of ethylene diamine was introduced here. I'll tell you why it was introduced, was added dropwise, and the final solution was placed into a Teflon line, for hydrothermal purpose, and then the final solution was placed for about 180 degrees Celsius for 12 hours, and the resulting solution was cooled down at room temperature, and then later on it was centrifuged for about I think 10 to 15 minutes. And what we observe is the supernatant, the larger particles were settled down, and which were dried in the tube furnace for about 12 hours and stored for further use. And what we observe is the supernatant is stored separately for further characterization and application. So we could able to get two different stuff here. One is the solution which is there, which is a normal clear solution which was observed. Then the other part was the supernatant layer, which is settled down, and then and when we characterize this, we could able to see that there are two different moieties was formed. So in the first case, the supernatant layer was found to be having a iron doped carbon dots, and in the second case, the supernatant layer which we found it at the lower base of it, which was settled it at the lower base, and that was found to be just a simple Fe3O4 iron oxide nanoparticle was found to be present in this case. So in one reaction, we could able to get two different products here. So after having this product, the important part is to characterize this product both when you work in the nanoparticles, nanotechnology, you have to emphasize on the morphological aspect and different various characterization aspects. So we have tried with to do the morphological characterization. We have checked the powder XRD followed by TAM, SEM as well. So the supernatant and the solid octane after synthesis were further characterized and to discover their size, shapes, and composition of both the Fe-doped carbon dots and as well as the iron oxide was done. So we could able to get a very clear powder XRD pattern over here, and of iron dope carbon dots shows the both large peaks specific for amorphous carbon structure, and the thin peaks which specify the metallic structure of FeO, Fe3O4. So some impurity peaks were also observed in the XRD pattern you can see here, and that can be, this can be due to the incomplete carbonization, and some residual groups from the precursor remain on the surface of the carbon dots. So that could be for, it can be assigned for that particular purpose. The XRD spectra of settled powder, if you see it, it shows us 6 peculiar diffraction peaks at 2 theta, at different 2 theta values. I won't go into the detail of this. So further, we have seen the TEM images of this. So in the TEM image, you can see for Fe dope carbon dots shows the majority of the spherical polydispersed particles, and the size was calculated and found to be between around 3 nanometer plus minus maybe 0.5 nanometer here and there. And you can see that the very diffused set pattern revealed the poor crystallinity of this material. And you can see the iron oxide nanoparticles are heterogeneous and also spherical in shapes, as shown in, you can see the lower one, the TEM image of that is the section 3 here, and you can see the lattice spacing for this is about 0.3435 nanometer, and the size distribution is between 16 to 24 nanometer was found for this particular iron oxide nanoparticle. We have characterized further by employing FTIR techniques, and in FTIR you can see a characteristic of OH stretch of hydroxy group is found, and OH stretch of carboxylic group was also found, whereas the stretching vibration of CH was seen around, you can see it at around 29-30 centimeter inverse. The stretching vibration of primary amines followed by phenolic OH bending is also found, which is due to the, attributed to the phenyl ring over here. So after having, the IR, we have looked at it very carefully, the XPS value of this, and which shows that, the iron which is present here, it is in the to confirm the oxidation parts of this particular iron, and also the successful doping of iron in carbon dot was particularly confirmed by using the XPS over here. So these are some characteristic characterization techniques which we have used to characterize both Fe3O4 and also Fe dope carbon dots before using it for further application. Then we have checked the photophysical properties of this particular characteristics of this particular carbon dots, that is Fe dope carbon dots and iron oxide nanoparticle. And we have employed UVVs and fluorescence spectroscopy. So the distinct peak at 345 nanometer in UV-vis spectrum arises due to the N to pi star transition at the edge of carbon lattice. And moreover, the low strength broad absorbance trail you can see towards the end till wavelength 550 nanometer. And as this can be, this can be assigned to the surface states of the carbon dot associated with the functional surface group, and which give rise to low energy sub bands, you can see within sub band gaps within NP star band gap. And so the aqueous light brown colored solution of Fe carbon dots, you can see Fe dope carbon dots bring about the blue light fluorescence, and visible even with the bare eyes on UV light irradiation. So if you just take up this solution and put it under UV lamp, you can easily see the transformation of the brown color solution, and seeing it as a very highly illuminated blue color solution. The same solution has then we have taken the emission spectra at 450 nanometer when excited using the light of wavelength about 360 nanometer. The surface state owing to the functionalization leads to the trapping of excited state energy, and we can actually tune it at different excitation, and we could able to get a very good corresponding spectra, emission spectra over here. Then after having excellent photophysical properties, we thought to explore the sensing behavior of this iron dope carbon dots. And so you can see the spectra 4A depicts the the fluorescence spectra of iron doped carbon dots, and in absence and in presence of doxycycline. So we thought to check this antibiotic doxycycline, whether how it is affecting and how we can whether we can actually detect this. And you can see a strong fluorescence peak at 450 nanometer, and by contrast of dox caused an obvious decrease in the fluorescence intensity. So as soon as you add the doxycycline solution to this carbon dot, you can see slowly with the various concentration decrease in the fluorescence emission was observed. So that means a quenching was taking place during this addition of doxycycline solution to it. Then further selectivity of iron, Fe dope carbon dot towards the different targets was also investigated, and you can see as in the below, you can see in presence of different similar agents compared to doxycycline. You can see the it is very highly specific towards the doxycycline. You can see this in the original in C and D. You can see the higher absorbed shows the intensity with the higher intensity compared to similar products. So sensing was very clear that it is highly selective towards towards the doxycycline part. And so by contrast, no significant decrease in fluorescence was observed in the presence of other target molecule. We have used such as Norflox, Lenzolid, Oflox, and Cefixime, and AZI. Different, we have taken a different antibiotics over here. So these results indicate that the proposed assay method possesses outstanding selectivity and specificity for DOX detection. And even in the presence of the analytes, our sensor shows an excellent selective detection of DOX. So to have its applications, or to see in the real life whether this sample can give you some, this probe can really work for a routine sample or daily life sample. So we used the proposed method to detect the DOX in raw milk and to investigate the applicability of the synthesized Fe dope carbon dots for DOX detection in real food samples. Our raw milk was spiked with known quantities of DOX, and afterward mixed sample were pre-treated and analyzed. And if you see the table present here, the recovery rates range from 96 to 101.5%, whereas the relative standard deviation range from 1.4 to 3.2%. This implies that the proposed detection method has good reliability and excellent accuracy, and moreover, the entire experimental process, including the sample pre-treatment procedure and analysis stage, it just required 1 hour, and indicating that our method can be used for rapid DOX detection in the raw milk samples as well. Then later on, we wanted to investigate the kitchen blender assisted degradation of doxycycline by using the other part of this, the sample which was formed during the synthesis, that is by employing the Fe3O4 as a catalyst. So here we have seen that doxycycline model pharmaceutical concentration recorded by using the UV spectroscopy. You can see the lambda max as 346 nanometer value decrease with the increases the shear force cavitation time using kitchen blender. And after just 5 minutes, we achieved 70.26% degradation of this DOX. That is, if you see the figure 1 over here. So within 5 minutes, we could able to degrade this particular, doxycycline unit over here. You can see the further degradation efficiency can be enhanced by increasing the shear force cavitation time. And if you see the concentration CO enhanced by increasing the interaction between the doxycycline molecule and the number of reactive species for a specific amount of catalyst number of in terms of active species. Then further to investigate and to compare the C by C0 versus T plot, whereas T represent the blending time shown in the figure 1B. If you see the figure 1B, so we can easily see that 70.26% while the degradation of doxycycline without any sample, and the remaining 11% after 5 minutes was also done. So after having this, so this shows that this particular both we could able to employ both Fe doped carbon dot as well as the iron oxide, which was formed as a nanomaterial. Both are very useful in terms of sensing doxycycline and in terms of degrading the doxycycline by using the Fe3O. So after having this, I'll just take up the second case over here. So next study, the hydrothermal carbonization was used. So here we have taken for the synthesis of bimetallic carbon dots here. So the synthesis was performed by heating the whole mixture. We have introduced here urea and silver nitrate and gold chloride, chloroauric acid here. And what we did, we have heated this for 180 degrees Celsius for about 4 hours in an autoclave using the furnace. And the heteroatom doping was done using different sources like gold and silver was introduced to this, and urea is used, and then we have bovine serum albumin was used as a nitrogen source for this purpose. So the quantum yield was calculated and found to be 50% in this particular case. So it was highly fluorescent carbon dot was observed over here. Then we have done the morphological characterization, and it was we have used order XRD, TEM, and FTIR, and it all gave us a very good signal that this bimetallic carbon dot has been formed here. And after characterization, we went for photophysical properties and to determine the optical properties of these bimetallic carbon dots. UV spectroscopy and fluorescence spectroscopy was performed, and the aqueous solution of BCDs shows a typical absorbance peak at 340 nanometer. And this peak emerges due to the NP-pi star transition at the edge of carbon lattice and occurs because of the energy transfer between carbon band and the dopant present within the carbon lattice over here. So these are the some characterization part, and so basically this significantly and also we have done some TCS-PC for which the data is fitted to the 3 exponential function, and this significantly shows the long lifetime of this bimetallic carbon dot or desired candidate, and this can be used as a nanoprobe for fluorescence lifetime imaging in many diagnostic applications. So after having excellent stability under various different conditions, we went ahead for sensing application. So here the carbon dots have dual ability to accept the electron as well as donating electron, which is responsible for quenching of fluorescence owing to the transfer of electron between the analyte and the carbon dot. The highly aqueous soluble, bimetallic carbon dots were checked for their sensing response towards the nitroaromatic compounds, and we have used a series of nitroaromatic. A strong optical response was observed in presence of picric acid only, and the fluorescence of BCDs was turned off as soon as you add the picric acid in the range of 0 micromolar to 500 micromolar. So as soon as you keep on adding the picric acid, you can see the quenching of this fluorescence of this bimetallic carbon dot has taken place, and therefore this is a gradual decrease is in the fluorescence intensity with the addition of picric acid. Sense that a very good linear correlation you can see can be formed over here, which is about 99% relation. And we could able to sense this picric acid up to LOD of 46, around 46 nanomolar solution. And you can see the pictorial representation in this last figure. You can see, so as soon as you add this your picric acid, you can see the turn off response is observed by the bimetallic carbon dots. Then the reliability of this analytical sensor for time application was checked, and using tap water for the laboratory. And as expected, no picric acid was detected in tap water. So what we did is, as expected, water samples were prepared by adding a different concentration of picric acid, and recovery test was performed. And you can see in the recovery test the range of the range at which it was formed is between the 93 to 97% was recovered, and the standard deviation was less than 2%. You can see as shown in the table 1. So this shows the very good recovery rate with accuracy and reliability showed the application potential for the BCD sensor to be used in the real sample as well. So after having this, we wanted to see the selectivity of this BCD towards the picric acid, and detection of and the sensing mechanism can be explored. So the selectivity of proposed sensor was checked by observing its fluorescence behavior towards the various analytes, which are picric acid, 3-nitrotoluene, that is, and then we have used 2,4-dinitrotoluene DNT, and 4-iodoaniline was used, nitrobenzene, and ortho-nitrophenol and para-nitrophenol, and 3-nitroaniline was used to compare the picric acid selectivity. And using the concentration of about 200 millimolar of each we have taken. So it is clear from the figure, you can see how it is specific. This particular BCDs are very specific towards the picric acids only, if you compare with any other similar molecule present here. And moreover, there is a clear overlap between the emission spectra of BCDs and absorption spectra of picric acid was found to be present in the figure B, if you can see it here. So no such overlap was seen with any other analytes and absorption spectra, which makes BCDs a very selective and selective sensor for the picric acid only. So we wanted to see what is the sensing mechanism for this particular moiety and how it is. So although there are some reports are already available on this, so we have further investigate the mechanism behind the turn-off behavior of BCDs. And in presence of picric acid, the optical properties of both picric acid as well as BCDs were studied precisely. And by looking at the overlapping of the absorbance spectra of picric acid and excitation and emission spectra of BCDs, the phenomenon behind the fluorescence quenching was expected to be either through fluorescence resonance energy transfer, that is FRET, or through inner filter effect, that is IFE. So it is important to mention here that the other nitroaromatics or aromatic compound used in this study showed a very less irrelevant spectral overlap with BCDs, and to investigate further, TCS-PC was performed and for the BCD solution in presence and absence of the picric acid. And what we found is the average lifetime of this has been reduced from 10.1 nanosecond to 9.94 nanosecond after addition of picric acid, as you can see in this spectra over here in the A figure A. The slight change in the fluorescence lifetime after addition of picric acid indicates that the quencher is not making any chemical bonding or forming any new complex with the fluorophore. The quencher picric acid is binding directly with the fluorophore BCDs at ground state only and exhibiting static quenching. So that is how. So therefore, in FRET, the fluorophore and quencher reacts chemically to form an intermediate product that is responsible for the fluorescence, quenching. So this is how we can say that the completely, the complete coincidence absorption spectra of picric acid with the extension spectra of BCDs, which further extended to emission spectra of BCD, and so this makes a very strong evidence for self-absorption process, and that is like IFE as the primary phenomenon responsible for the fluorescence quenching. We could able to confirm this. So after having these sensing properties and excellent photophysical properties, we wanted, since there was a presence of gold and silver both in this, so we wanted to check what will be the effect, whether that will affect any antibacterial study properties over here. So keeping that in mind, we have actually done some antibacterial studies here. So to demonstrate the antibacterial studies, we used the E. coli, that is DH5A was used. So the optical density measurement method OD600 was utilized to verify the photoactivity bacterial cell growth inhibition by BCDs, and the results shown you can see in the figure 11A revealed that the considerable effect of BCDs with the light irradiation on E. coli cells, the growth of cells treated with BCDs alone was inhibited, and in comparison to the control cells. However, light exposure further enhances the antibacterial nature of BCDs, and confirming that the photodynamic antibacterial activity is happening over here. The carbon dots you can see in the figure B, when absorbs light, the electron jumps from valence band to the conduction band, and which leads to the generation of electron hole pairs, and this electron reacts with available surface bound oxygen, whereas the holes as oxidant reacts with OH minus present in the system and lead to the formation of hydroxyl radical overlay. And this can also lead to the ROS binds with DNA, RNA, and cellular proteins and damage the essential components of the cell, which proves the lethal for the bacterial growth over here. So if you see the oxygen generated by BCDs upon photo irradiation and reacts with DPBF and results in decreased absorbance at 414 nanometer with each exposure, and you can see the data collected after light exposure with 5 seconds interval and were plotted and shown in figure 11C over here. So this is how you can see that the overall periodic decrease in the absorbance value inferred photo-induced singlet oxygen generation was observed by using this BCDs in the DCM. So finally, I'd like to conclude my talk. That we have demonstrated the 2 nanopo material, that is Fe dot carbon dots and Fe3O4 nanoparticles over here, and which was synthesized simultaneously and was employed for sensing and degradation of doxycycline here. And then secondly, a bimetallic doped carbon dots was prepared by one-pot hydrothermal method over here. And as synthesized carbon dot exhibit excellent quantum heat of about 50% with excitation independent emission behavior, and a very good aqueous solubility along with an excellent photo and thermal stability was observed over here, and that was further used for picric acid sensing as well as antibacterial studies was checked by this particular bimetallic carbon dots. Finally, I would like to acknowledge the funding from IIT Indore, SERB, CRB, BRNS and CSIR for this particular work, and thanks to the Sophisticated Instrumentation Center IIT Indore for characterization facilities, SAF IIT Bombay for HR-TEM imaging and FTIR, etc. And finally, I'd like to thanks to my group members. We are still not fully recovered, so waiting for a full-fledged 2022 picture very soon. Thank you all for your kind attention.
Yeah, thank you, Dr. Sheikh Mubin. The same discussion, there is Dr. Ranjan Shah is waiting for a longer time. Dr.
Sure.
Ranjan Shah, yes.
Thanks, Dr. Mubin, for excellent talk.
Yeah, thank you.
So I have a few questions related to the mechanism on which you have this selective detection. The given
of chemistry. He is also editor of the book series on atoms, molecules, and clusters, structure, reactivity, and dynamics. Professor Chattaraj received several awards and medals. He is the fellow of all the three Academy of Sciences, Indian Academy of Sciences, Bangalore, National Academy of Sciences, Allahabad, and Indian Academy of Sciences, New Delhi. He received J.C. Bose Fellowship in the year 2019, and he also received CRSI bronze medal and also a silver medal. With this brief introduction, may I now invite Professor Pratim Kumar Chattaraj to deliver a lecture on systems and processes in a confined environment. Professor Chattaraj, the floor is yours.
Okay. Can you hear me? Am I audible?
Yes, yeah. Yes, you are audible. You can move one slide up and down so that
okay.
Yes.
So good afternoon, everyone. At the outset, I would like to thank the organizers, especially Srikanto, for kindly inviting me to be a part of this endeavor. And as Srikanto has told me that I should start from the very fundamentals. So I will try to start at a rudimentary level, and gradually I will catch up with the state-of-the-art research. And I would request Srikanto to help me in changing the slides. So here in this talk, actually I'd like to tell you what is the effect of confinement on various systems and processes. So as you can see, so I'm talking about the confinement, I'm talking about systems, I'm talking about processes. So first of all, I'd like to introduce you to those terms. Next. So when you talk about a system, so I take the language from thermodynamics. It is just a part of the universe where we have a special interest. And it may be, depending on its characteristic, it may be isolated, closed, open, etc., etc. And when you try to describe a system, you talk about its structure, stability, properties, bonding, interactions, etc. And there are different types of systems having different length scales. Some may be like quarks, electrons, protons, atoms, molecules, going all the way up to celestial bodies. And depending on that, obviously, your experimental and theoretical techniques would get changed to understand that particular system. And a system is generally characterized by a potential, basically, that defines the state of the system. When I say the potential, in thermodynamics, we say any thermodynamic potential. It may be, say, entropy, Gibbs free energy, Helmholtz free energy, everything which you can write as a simple function in terms of the system variables like temperature, pressure, say number of moles of a given component of a system, etc., etc. Now, when you talk about this length scale, obviously we start from say something like very crude like molecular mechanics, and then we go to say classical mechanics or quantum mechanics, and a very large system you have to bring in the relativity as well. So depending on, and in some places obviously you can get a given system, you have to treat in a different say fashion, so you can mix those and get like quantum mechanics and molecular mechanics, you can couple them, or you get techniques like Onium, where you can have a lower level quantum mechanical calculation somewhere in the higher level quantum mechanical calculation in some part of the same system. Then we go to a process. Process means it's a dynamical one, so which takes you a system from one state to another. And again, so what we are talking about, if you go from system to a process in understanding, this is like from being to becoming. So there may be again different types of processes, isothermal, adiabatic, isobaric, etc. And there are various time scales. Like some of the processes may be very, very slow and some may be very fast. So obviously you cannot apply same type of theory or same type of computational technique in elucidating two types of processes. And you can do again quantum dynamics, classical dynamics, or even simulations like molecular dynamics, all those aspects. And here, when you have a process, it takes you from one system to the other, and which way it will go, which way it is spontaneous at a given condition of, let's say, temperature, pressure, etc. That is governed by the potential difference. And in general, you have a flow from higher potential to the lower potential, and this would continue until the corresponding equilibrium is attained. Yes, I can tell you one case only when you don't see, even if your potential difference from higher potential to lower potential, it doesn't flow. It is like money doesn't flow from a pocket of a rich person to a poor person without any bias. Now we go to thermochemistry, where we will see that a chemical reaction, let's say a thermochemical reaction, and it may be exothermic, where system's enthalpy increases, that means that the heat is coming out, and it may be endothermic, which is just the opposite of that. And in this case, what happens, so if you see how the system behaves, so if you have chemical reaction, that will continue. Also, in addition, and sometimes you may not have chemical reaction, but only the phase change you can see, and you can talk about a phase diagram, and depending on the corresponding temperature and pressure, and sometimes also the concentration, etc. You can see they are in various phases like solid, liquid, vapor, etc. Next. So today I'll just take a specific example in order to tell you something what I will go into when I would like to tell you regarding the typical confinement effect and why at all we are interested in doing that, and what are the other features associated with that, and extra new items what we are planning to present. In Haber-Bosch process, the first thing what is known, you know, the Haber, in fact, thought of a given philosophy because you know that he wanted to prove the Malthusian theory to be wrong. So Malthus proposed that the geometry, say the population increases, say in a geometric progression, whereas the productivity of any field increases in arithmetic progression. So it is the fait accompli. Those two curves will cross somewhere, and you will have the famine as the result. So no one can predict. Obviously, the advent of high quality seeds, fertilizers, and other irrigation techniques, etc., they prove the Malthus's theory is not exactly right. And the fertilizer came as a boon. And you will see that majority of the fertilizers, they are nitrogen based, and ammonia is the important say ingredient in getting that. And in order to have economically say viable technique, it was thought of by Haber that you get from all natural sources like nitrogen from air, hydrogen maybe from some natural gas like methane, and then try to produce ammonia out of it. But there are several problems in order to understand this. But even the Haber's process, I will come with the development, and that is important in understanding what I am going to tell in the later part of my talk. Why I am telling this, that there is a kind of competition that in the last 100 years, say in 20th century, what was considered to be the most important discovery, and you know that there were competitors were quantum mechanics, relativity theory, then you had Watson-Crick model of DNA and all sorts of stuff. But here, the penicillin, and here you can see that obviously at the top, the winner was the Haber-Bosch process, considering its societal importance. And in this situation, what happened, what he thought of, that somehow we have to have a specific methodology to convert nitrogen and hydrogen to ammonia in this particular method. But before going into that, let me tell you that he was a genius. He was given Nobel Prize, and later on Bosch joined with him. He was basically an engineer, so his input was also important to make the process economically viable. But ammonia is also the precursor of explosives. And not only that, although he was respected as a scientist, he was one of the most hated scientists in the world. Haber was considered to be basically the father of chemical warfare in Germany during World War II. And this is something what caused havoc in his family. Several of his family members committed suicide because of the hatred what they could see from the other people in the world. What is the problem with this conversion? The first thing you can see that the reaction he wanted to explain in terms of La's Atelier principle, so which is like homeostasis in biology or price equilibrium in economics. What it says that if you just simply perturb a system behaves in such a way that it will try to minimize that perturbation or to nullify that perturbation. And that is the starting point in this case. So the reaction is basically exothermic. If the reaction is exothermic, you know that if you simply decrease the temperature, then only the reaction would get better. But there is a tug of war. Now, when you decrease the temperature, you know from say simple Arrhenius type equation that the rate also will go down. So if you want to favor the thermodynamics, kinetics would get the impediment. So in that case, what will do? You'll have to have a balance. So it was shown that around 400 degrees Celsius, if you consider, so this would be a balance, but still the rate is not that high. But still thermodynamically it is favorable, but rate is not very high. Then he considered that we need to have a kind of catalyst, and that will enhance the rate of the reaction. So in this case, he obviously considered that was very popular in those days, that some metal catalyst would be there, and he considered osmium, and he had shown that with osmium you can get a very good yield. But the osmium, first of all, it is not easily available. It is, say, very expensive, and it is highly toxic because it's a heavy metal. The other alternative he suggested was uranium, which contains all the drawbacks of osmium. In addition, it has the problem of the radioactivity. Now, this is something. So, luckily, you know that the catalyst will change the reactions, but it will not have any effect on the thermodynamics. So, the equilibrium constant or equilibrium concentrations will not get changed, so that you don't have several knobs to just handle. In this case, he consulted Bosch, and he came up with something like alumina supported iron, which perfectly fits the bill. Only thing that it solves three problems. One, obviously, it is not that scanty. Second, it is not that expensive. And third, because it is not that heavy metal, it's not very, very toxic. Now, today, so you can see the catalysts play a very important role in understanding this. But now you are going from heavy metal to light metal, then you go for metal-free catalysts, like several organocatalysts or frustrated B-square. So, there are many catalysts which are known today, which doesn't contain any metal. But I am going to introduce you to some place where you have the catalysis, but there is no catalyst. And this is something what is basically the major subject matter of today's talk. Next. Next. Okay, so I will tell you some important physicochemical problems. First, I will talk about bonding, interactions, dynamics, reactivity, everything, say, amalgamated together, electronic excitations. And there you will see that the subject is basically, you have to treat it in a holistic sense in order to understand the effect of confinement. So first I will consider the atoms or molecules when they're having collision with the proton. In fact, we considered two processes. One is the collision process, another is the interaction with some external electric or the magnetic field. Actually, those are the processes which simulate a chemical reaction. So we wanted to analyze applying, say, first proper ab initio quantum dynamics, and we wanted to understand what is happening during the process. If you have confinement or if you have electronic excitation, what happens to the reactivity, what happens to the bonding, and so on. So next. So what we did first, you can see that we tried with ground state as well as the say electronically excited state, and we tried with some reactivity parameters and reactivity principles. What it says that a system is more stable when it is harder and it is less polarizable, and a process is more spontaneous if it is accompanied with increase in the hardness and decrease in the polarizability. So what we wanted to check that when you have a chemical reaction, let's say some helium atom is getting collided with H plus to give you HEH plus molecule, in a dynamical framework where exactly the reaction is going on at the point of attack where the HH plus is getting formed, you can see that the hardness gets increased and polarizability gets decreased. And that is basically the dynamical variant of those principles, maximum hardness principle and minimum electrophilicity principle. And we can see the excited state versus ground state. What it says that when just you have the electronic excitation, obviously the system will be more reactive and less stable. So accordingly, if you measure the height of the hardness and depth of the polarizability profiles, that will reflect that excited states are more reactive. And not only that, here we could do the confinement also. Confinement in the sense, say, when we allow the proton to come to the say target, and there we don't allow the corresponding say electron density to go beyond certain, it is having the axial symmetry, the cylindrical symmetry, the radius of the cylinder, I can choose to make it larger or smaller, and accordingly I can in the system. And that is also reflected over here. If you confine a system, in general, it gets more stabilized. Okay. And another important aspect here is that if you talk about the simultaneous application of excitation and the confinement, you can do a havoc. You can get the ground state behavior from excited state. You can get excited state behavior from a ground state of a system. And this is something what I think experimentalists would try to do it now, because theoretically we have shown that this is a lucrative way of looking into the processes which you can handle simply applying your common sense and this high-level computation. Next. And then we wanted to see the regioselectivity also. So we have shown that suppose if you have the molecule and proton collision, HF plus H plus, if it collides from say hydrogen side, it will give you H2F plus, and if it collides from fluorine side, it will give you HF H plus. And both of them, if you just now compare their hardness and polarizability values, we can immediately tell, at least kinetically, which particular product would be more favorable. And that is typically the regioselectivity present. We have done some slightly complicated system as well, but at this moment, I don't want to go into the details. Next. So next. Next. So now we will show the confinement-induced binding of noble gas atoms. So next. So what I'll show you that suppose if you take a cavitant, okay, and then you put some noble gas atom. The first thing what we could see that noble gas atom as such inside the cavitant is not a very stable system, but once if you can repair it, it was experimentally shown, then it requires too much of energy to come out of that, and accordingly it will not come out and it will be inside. So this is point number one. Point number two, if you place not one, but let's say 2 or 3. So I'll talk about only 2 at this moment. So next, next slide. Next. Yes. So if you consider now 2, and this is, you can see that we have shown also the time evolution in a, we did some kind of simulation, molecular dynamics simulation, and there what you could see that those 2 atoms, as if they are forming a molecule, and they are executing some motions. We could identify their vibrational and rotational motions also, typical precisional motions. And those 2 atoms, it's not that they are moving separately, but they are moving together in tandem, as if it is a diatomic molecule. Then we did, of course, their typical bonding analysis with standard techniques, and that tells us that it is basically having a kind of partially covalent bond formation between the 2 noble gas atoms. So it is something like the confinement can induce marriage between two unwilling partners. So 2 noble gas atoms will form a partially covalent bond if they are confined. And we can study also that motion of this as kind of a diatomic molecule inside that cavitant. Next. So exactly, it is in some other case. So you go to the next. So you'll see some Ng2 molecule, and it is in some other type of cavitant. So we can analyze their typical motions, the vibrations and rotations. Next. So here I will tell you something which will have a relevance later on. So here we talked about a molecule, the cavitant, that itself has some unique characteristics that I will tell you later. And inside this, if you have two noble gas atoms, as usual, so we have seen like fullerenes and other BN fullerenes, etc. Here also, in this, this is basically borospherine, and this is just the boron equivalent of fullerene, and inside which, if you put two noble gas atoms, they will behave like a diatomic molecule. And here you can see that if you take one atom outside and put one atom inside, that is more stable than putting both of them together inside. But what you can say, once you can form it, maybe under high pressure, that was done experimentally, then it is very difficult because it will have to cross a high energy barrier in order to reach that particular stable state. So it just attains a kind of kinetic stability, and this will be there, which can be probed experimentally. Next. But I will come back to this later to tell you about the specific behavior of borospherine. So we did also with other cavitants like cuprobutyrol. So this is just for the sake of completeness. I'm telling you something. Next. So this is again the same cuprobut 6-uvil. Next. And we have studied different types of molecules inside that. And we have shown the effect of confinement on those molecules, the activation, etc. Next. So we wanted to study whether confinement will always lead to thermodynamically and or kinetically favorable reactions. So this was a kind of invited perspective article. So where we analyzed thoroughly, and it would be clear in next couple of slides. So go to the next. So what we could show that we had taken say two different simple chemical reactions. I will show you one over here. We have studied several reactions inside the cavitants. This is just Diels-Alder reaction, and we have taken two different. So there is the free reaction and two different confinement media, EX-Box4 plus and CB7. And there you will see that when the reaction proceeds, we studied both thermodynamic and kinetic parameters. So maybe in the next slide we have a table. Next. So no, this is a kind of again invited perspective on the bonding reactivity and dynamics in confined systems. So next, so maybe, yes, it is there. So what it says that in comparison to the free state reaction, you can see in one of the cavitants, it gets 3 orders of magnitude, the rate is getting enhanced. So that means it is really catalyzing the reaction, but we don't use any catalyst per se. And thermodynamically also it is becoming more favorable. On the other hand, if you put it in the other cavitant, the system is getting decelerated. And not only that, it is, say, not becoming more favorable as well. So in this case, what we can say that depending on the nature of the reactants, depending on the nature of the cavitants, it is having electronic effect, it is having steric effect, all of them coming together, behaving in such a way that will determine whether it would be kinetically favorable and thermodynamically favorable, or it would get catalyzed or not. So there is nothing like blanket prescription that whenever there is a confinement, it would be thermodynamically favorable, more favorable, or it would get, say, accelerated due to confinement. It is not true. And if you change the reactants, again, you can see the reverse behavior. In that case, like EX4 plus will be facilitating, not the solution. Next. Then you can see the bonding we have shown. We have seen the catalytic activity. We have seen the thermodynamic activity. We can talk about optoelectronic properties, how they are going to get changed. So next, so if you do the functionalization and do the guest encapsulation, we could show that orders of magnitude change again in the polarizability and hyperpolarizability or second hyperpolarizability values. That means you can, in principle, try to create the typical nonlinear optical material within a confined environment, which was not maybe or maybe a weak NLO material. You can prepare the better material through confinement. Next. We will switch over. So these are the alpha, beta, and gamma values. Next. Now, these are the important aspects, say what we wanted to check, the host-guest interactions. So we studied various cavitants here. It was only EX4 plus. And there we basically tried to check that we can, in principle, solve one is the energy crisis, another is the environmental pollution. So if you can just think about the fossil fuels, basically they take enormous amount of time to get formed, but it takes relatively much less time to get totally consumed. Not only that, when you burn a fossil fuel, it will create environmental pollution because of the greenhouse gas. So what is the alternative? So people have been thinking about hydrogen as a fuel because it is abundant in nature. And second, when you burn hydrogen, it forms innocuous water vapor. So it can solve two problems at the same time. And the major trouble comes, say hydrogen being the lightest molecule. In this case, what will happen, say suppose if you want to think about some automobile driven by hydrogen fuel, then the container which you require to have the hydrogen stored in order to run the automobile, it would be larger than the size of the automobile itself in order to run even maybe 1 kilometer of the road. So you need to have the proper strategy for the hydrogen storage, and you require hydrogen storage material. And obviously confinement is very, very important in that case, or typical interactions. And there you have to talk about many different aspects, like they should be thermodynamically, say first of all, gravimetrically, they should be economically viable, volumetrically viable, and say thermodynamically and kinetically, they must be reversible. Reversible in the sense that if it is too strongly bound, like in chemisorption, obviously you will have to apply extra energy in order to get that back. If it is too weakly bound, like physisorption, even simple air can take away the hydrogen from your storage material. So the interaction energy should be somewhere in between the energy of physisorption and chemisorption. Kinetics wise also, the desorption kinetics should be very fast. Adsorption kinetics also should be very fast. So you have to have various components at the back of your mind when you design any hydrogen storage material. So next. So we have shown say hydrogen storage in this. So next. We have shown in octiacid cavitant also. Next, it is just only different types of systems, different reactions, different cavitants. So this is the octiacid cavitant. So next. Now, we again consider the encapsulation of small gas molecules and rare gas atoms inside that cavitant. Next. Next one. Yeah. So these are the pictures. So you can flash on. Next. Now, when we talk about the chemical reaction simulated by the interaction of an atom or a molecule with some external electric field. We'll talk about the magnetic field also. So we see what is the effect of confinement. We have also seen the effect of electronic excitation. So you can see several aspects that intertwined together in order to see their combined effect. Next. So this is the electric field, how it is changing, and when you talk about that, you can see the chemical potential of the system, say, oscillates with external field at even lower strength, but the hardness requires much higher, say, strength of the electric field, because it's the second order variation in order to have the in phase oscillations. Next. Yes, next. Now, we studied various types. So this is just a snapshot of different types of hydrogen storage materials, like clathrate hydrates, boron nitrogen clusters, etc., etc. You can see. So the star-like molecules, super halogens, super alkalis, and all sorts of stuff. And some of them at least, they are very good candidates for effective hydrogen storage materials. Next. Then we wanted to study that whether we can bring in other external, say, handles in order to improve the efficacy of the hydrogen storage. So here we have shown that hydrogen adsorption process, we calculated and generated the temperature pressure phase diagram, and we could identify the temperature pressure zone where adsorption is favorable, where desorption is favorable, and where they are in equilibrium. That means you can choose the temperature and pressure of the system in such a way when you would like to absorb the molecule. So you are filling, say, your container in the gas station, and when you would like it to come out to actually start your automobile and run it, then you go to the corresponding desorption temperature and pressure. So you can, in principle, handle this, and we'll see in the electric field also you can think about. Next. So this is applied electric field, and applied electric field also can do the same job. So you can have several such handles and knobs which you can just rotate in order to satisfy your requirement. Next. So now we'll switch over to a type of systems which are dynamically stable. Dynamically stable means their stability is like that of a bicycle. That means they are stable when they are in motion, they are unstable when they are static. So the concept of the rigid molecule and its connection to the stability is not at all sacrosanct today. There are several molecules, in fact, which are stable in their dynamical condition. And it is not new. So today we know several such systems, but it is not new. You know, Kenneth Pitzer did it in early 50s, showing in order to explain, let's say, the IR spectrum of cyclopentane. He had shown that if you consider it to be a planar, say, regular pentagon type structure like D5H structure, obviously that will not give you the proper spectrum what you would expect. Rather, what he had shown that it is like some half envelope type structure where one of the 5 carbon atoms would be above the plane and remaining 4 will be on the plane. But again, you have to apply the democracy. So which one will go up, you cannot decide. So they themselves decide. So one goes up and it comes down, the next one goes up, and then again it goes down and the next one goes up. And ultimately it behaves like as if a twist or a kink is rotating around the ring. And this is what is called the pseudo-rotation. And that pseudo-rotation is a degree of freedom, and that is reflected in the corresponding IR spectrum. In fact, there are molecules like bulvelin, which have so many different structures. People say that the molecule bulvelin doesn't have any structure at all. So here we will talk about a molecule, and most of these molecules are basically boron-containing molecules, because the boron has the propensity of showing multi-center 2 electron bonds, because the first such 3-center 2 electron bond which we came across in our schools was typical banana bond in dihydrogens. So you can see that these boron clusters basically they behave like a Wankel engine or a Wankel motor. So you can see there is something like one inner wheel which is rotating apparently relative to the outer wheel. There are not many boron clusters which exhibit, and this is the motion what is called fluxionality. So these are fluxional molecules, and you can in principle play with these structures, and even if you add one or if you take out one, you can drastically change a fluxional molecule will become non-fluxional and vice versa. You can apply external electric field to create that. You can increase the temperature of the system to create that, either to stop or to start the fluxional motion. So in order to know both the structure as well as the dynamics of these dynamically stable molecules, you need to understand several aspects, but I can tell you this is still in its infancy. Whatever little is known, I will tell you today. So this is the molecule what you have seen. Perhaps you didn't say pay any notice that the inner wheel was rotating relative to the outer wheel. So maybe in the next slide you can see that. Next, another molecule you can see. Okay, now you can see that inner wheel is rotating relative to the outer wheel. So what is happening? Basically, the bonds are continuously getting broken and getting formed, and this is possible only because of the multicenter to electron bonding. And you have apparently two rigid structures, and they are connected deeply so that one can rotate relative to the other. Next. So no, just one before. So can you go before once? Let me tell you one thing. One before. Yes. So in this case, what you can see that the molecule what is rotating, that is preferable, because if you consider this bowl-shaped molecule and you consider the say if it has a kind of inversion to go to the bowl in the upside down, that barrier is much larger, 6.7 kilocalorie per mole. On the other hand, this rotation of inner wheel relative to the outer wheel, this is only just a tiny 0.1 kilocalorie per mole. So the molecule prefers the typical pseudo rotation rather than having the inversion to the other side of the wheel. Next. This is basically we have done Born-Oppenheimer molecular dynamics simulation at 900 K. That means if you you just simply heat the molecule at 900 K, it will start exhibiting that fluxional behavior. Next. Then we wanted to see, say, if you have a molecule and then you add a kind of extra atom to it with this boron cluster, whether still it will just follow this. So not all atoms will be, some of the atoms, like we started with cobalt, iridium, etc. And there we could show that some of the atoms, they have propensity of preserving the fluxional behavior in this particular cluster. Next. Now what we did, we started with this particular molecule, which is in fact the borospherine, which I told you before, the boron equivalent of the fullerene. So at ordinary temperature, you don't see any kind of motion in it. But if you increase the temperature, you can see that it starts behaving in a different fashion and it exhibits fluxionality. In this case, the fluxionality is like this. In case of fullerene, you have alternate 5-membered and 6-membered rings. In case of this borospherine, you have alternate 6-membered and 7-membered rings. Here, what happens? The 6-membered rings are getting converted to a 7-membered ring, and 7-membered ring is going to get converted to a 6-membered ring, and that continues as long as you have that temperature. And this is what is important. This is basically giving rise to the fluxional behavior through the transformation of 6-membered to 7-membered and vice versa. And as you'll see that if you increase the temperature, the degree of fluxionality also gets enhanced as expected. So we calculated kind of mean square deviation, etc. And that will show that if you increase the next, maybe in the next slide it is there. Next. No, it is not there. So that will basically show you that you increase the temperature, basically the degree of fluxionality will get enhanced. Now what we did, say I talked about say putting one atom like cobalt, rhodium or iridium. Now we thought that if you put another diatomic, let's say carbon monoxide or nitrogen, then you could see the global minimum structure is basically like an umbrella, and this also exhibits fluxionality. So it behaves like a spinning umbrella. The bottom panels will show the spinning behavior, and this is the typical fluxionality present in this type of systems. Next. Yeah, so you can see the fluxional behavior. Okay, before I go into this, let me tell you, in certain cases, what happens, say, you may have, if you do the regular electronic structure calculation, you can see there are maybe 3 or 4 minimum energy structures, which are within a very close energy window. That means if you supply a kick, the molecule will go from one structure to the other, and that will have the ramification in the form of the fluxionality in the molecule. In fact, there are certain systems where 3 or 4 structures are there within their 0-point energy. So you don't need any extra energy from outside because it is inherent in the molecule itself. And automatically, without supplying any energy, the molecule will keep on going from, say, one structure to the other, and from the outside, you see the molecule is dynamically stable and it is exhibiting this particular behavior. So there is some experimental evidence also, the photo detachment infrared spectroscopy, and when this was done by this B13 plus molecule, which was studied before also, that it is a fluxional molecule. And if you do the electronic structure calculation and consider the 4 low-lying minimum energy structures, and you apply your common sense and get the corresponding spectra of those molecules and superimpose them, obviously that will not explain the experimental spectrum at least a couple of peaks. But if you just incorporate additional pseudo-rotational degree of freedom, it can properly fit the bill, and it can, if you do the BOMD simulation, it can reproduce exactly the typical experimental spectrum. Maybe it is there in the next slide. Let me see. Next slide. Yes. So you can see that if you add that extra peak, and also if you do the BOMD simulation, the experimental spectrum can be reproduced. Now, what I wanted to tell you that time, that you have seen that a cavitant basically can, in principle, catalyze a reaction or make it a thermodynamically favorable reaction, or cause, say, bonding between 2 unwilling partners, etc. And you have different types of interactions, different types of bonding, and so on. If the cavitant is also fluxional, that means in addition to the confinement, if you have this extra degree of freedom, can you make changes in the outcome as far as the catalytic activity, etc., bonding, etc. are concerned? And that itself is, I think it is worth exploring. I think there is a slide. So next slide. Yes. So we have published some perspective article that whether this is possible, and we have a kind of prognosis of the hypothesis that you can, in principle, inject fluxionality in improving the catalytic activity. Proper injection of the fluxionality of the cavitant and properly, in addition to the confinement, say with the proper say cavitant and proper reaction partners, you can, in principle, say increase the rate of a chemical reaction separately. Next. So before I conclude, say I'd like to thank my say funding agency, J.C. Bose National Fellowship and Indo-European Union HypoMap project. I thank my students and collaborators for having those materials ready, and also I'd like to thank you all for your kind attention. Thank you.
Yeah, Professor Chatterjee, thank you very much for the nice lecture. And now the seminar is open for discussion. There are questions in the chat box. I will go ahead with one by one. Is there any bond breaking and bond formation involved due to the rotation of outer and inner molecular cluster?
Bond breaking and bond making due to?
Due to the rotation of outer and inner molecular cluster.
Yes, bonds are getting formed and getting broken continuously.
Okay. There is one question from Professor Sujit Rai. Yeah, has the stability of methane hydrates at various temperature pressure been investigated theoretically? If yes, can you please elaborate on the behavior of methane in hydrate matrix?
Actually, what happens, you know that water cluster, methane is a stable molecule, forget about that. But water clusters at ordinary temperature and pressure is not a very stable system. But it was shown that if you place any arbitrary small atom or molecule inside that, the typical interaction of the system, what is there inside the embedded system with the cavitant, it will just simply increase the stability of the cavitant. So what it was shown that when actually we also did some work on that, say water clusters are considered to be very good agents for hydrogen storage. But you cannot store hydrogen within the water clusters because that itself is a very unstable system. But if you just simply put one methane molecule inside the water cluster and then if you try to store hydrogen molecule there, it would be a fantastic, say, low cost and environmentally, say, conducive hydrogen storage material. That people have shown, and not only that, now within say high pressure, people could show that you can form chunks of methane hydrates under the sea. So that is quite possible. So methane is basically giving stability to the water cluster, the cluster hydrates, but other systems also can give methane hydrates because methane is a natural gas. So naturally you can get methane hydrates which are being obtained from under the sea.
Yeah, Professor Sujit Rai also complimented that very happy to see the fluxional systems. That is comments from Professor Sujit Rai.
No, yeah. Why is they happy?
No, very happy to see the fluxional system. So that if Professor Sujitra is there in line, then he can interact with him.
Yeah.
Yeah, he is in chat box, but he may be busy in other meeting. Maybe parallelly there is so many things are going on actually. So being the new institute, so they have to take care of so many responsibilities. That is that. Yeah. Any other questions from colleagues from across India? Yeah, Professor Chatterjee, thank you very much. If no questions, kindly join along with me in thanking Professor Pratim Kumar Chatterjee for the wonderful lecture. And on behalf of the organizing committee, I thank you once again.
Yeah, thank you so much. Thank you.
Yeah, I also hand over it to Dr. Akhilesh Kumar Singh. Akhilesh?
Yes.
Yes.
So actually, Kaushik will take over. Kaushik?
Kaushik will take over. Yes.
Yeah.
Okay, all right.
And no, before I finish, before Kaushik takes over, I must thank Kaushik and Shrikanta for helping me. Otherwise, even say couple of hours back, I was hesitant and I was apprehensive whether I would be able to really talk to you people, because they helped me. So I could not enter through team.
But it was very nice talk, sir. Very nice talk.
It's very nice.
We could not understand completely, but yeah, whatever we could understand, that was really very nice.
No, but I am telling you one thing. I didn't show you any kind of equation, no quantum mechanics, no say equation, nothing. So no calculation. I have told only the facts. That's
yes.
it.
Yes.
Yes.
Okay, thank you very much.
Thank you.
Professor Chakra, the speaker. Thanks to Universal, there. And it was really a nice session, technical session today. And I invite you once again all join us tomorrow, 9:30. And until then, take care and good. Thank you.
Thank you.
Bye.
Bye-bye. So, Srikant.
Yes, Achilles.
Chalo. Tomorrow then. We will meet tomorrow now, huh?
Yeah, so we will meet tomorrow. So you may join at 9:15 or 20 because little early is going to be better.
Okay. Tomorrow 9:50. At what time it starts?
9:30 we are starting, but we'll begin at 9:15 onwards sometime.
Okay, ठीक है. By 9 or 9:15 we will be ready.
Yeah. No problem. So I'll be there. And thank you, Dr. Rajan. Okay, being there. Okay, then okay, Oculus. Then see you tomorrow.
Yeah. Thank you. Bye bye.